Hello, everyone. Welcome to the first inaugural wasmCloud Innovation Day. We are super excited to have you all here. Just to start off, I want to do a huge round of thanks to everybody who's attending the event on the Zoom webinar, everybody who's watching the live stream, and all of you who are going to be watching the recording after this. Continuing on with that theme, I want to give a huge thank you to everyone who has contributed or is a maintainer of the wasmCloud project. I have been working on wasmCloud for the last 5 years, and it's a huge honor to be able to work with all of you on this awesome WebAssembly project. So just to give you an idea of what the day is going to be like, we'll talk a little bit about the agenda and celebrate the progress that we've made, both in terms of the wider WebAssembly ecosystem, but also in terms of the evolution of the CNCF platform. We are going to go through technical deep dives in the latest innovations in wasmCloud and go through a couple of sessions where we'll go through our regular Wednesday weekly community call, wasmCloud Wednesday. We'll have a community keynote from industry leaders in the Bytecode Alliance and the WebAssembly ecosystem. And then I think we'll all have earned our lunch by then. Now, afterwards, after all of the sessions, we are going to be doing a co-working and workshop session in gather.town. The link to join this after the event is going to be wasmcloud.com/gather. We'll make sure to share this out, but I think it's going to be a lot of fun for us all to just get together in a kind of virtual office. You'll be able to meet the maintainers of wasmCloud. You'll be able to meet industry leaders in the Bytecode Alliance. We'll all be hanging out there, and it should be a great time. So just to give you an idea of what the morning session is going to look like, we'll have our welcome and opening keynote from Bailey Hayes. We will go through a couple of wasmCloud technical deep dive sessions and then talk about how the extensibility of wasmCloud has enabled us to add many different custom capabilities to the project and how that all works. Then we'll go right into our weekly community meeting and then community keynote. And then after the fireside chat, we are going to have multiple different real world use cases and demonstrations from Doug Rodriguez from Akamai, from Yakin and Tyler from Machine Metrics, and Colin from Adobe. They're going to be talking about what they've built and how they use wasmCloud today. And again, we'll go to lunch. So just to really nail this point home about how active wasmCloud is as a project, thank you so much to everyone who contributes essentially every day at this point. And I think that this has really propped up wasmCloud to be the project that it is today. Our weekly community meetings are vibrant. You can see, I know that lines of code is, a metric to use for a project, but you can see just the raw activity that wasmCloud has been going through over the last even just year has skyrocketed. So without further ado, I'd like to introduce Bailey Hayes, who is the technical steering director of the Bytecode Alliance, the WASI subgroup chair, and the CTO of Cosmonic. So Bailey, take it away.
Thank you, Brooks. Glad to be here. Really excited to see so many faces joining us for the first time with wasmCloud. I wanted to start the day off by talking about some of the problems that we're looking to solve with wasmCloud. And that begins with some of the pitfalls in modern platform engineering. To start, we kind of need to define platform engineering. So the platform engineering as a practice really began during the containerization era and the epic of compute, where first we started with microservices, we bundled those into VMs that allowed us to build out data centers and eventually moved to the public cloud. But really, there was this major paradigm shift that happened when we were able to package our applications into a container and then orchestrate those containers with Kubernetes. And that allowed infrastructure teams to evolve, to be part of the team that's providing a platform and giving common application services like capabilities from secrets management to authentication and authorization that then application developers are able to build on top of. And really, this was a massive improvement in our productivity and the types of things that we're able to build, but it does come with some pretty big problems. Namely, that building applications today are just too expensive to build, maintain, and run. And that really starts with the initial application language choice. And using that app effectively template that we build for all of our different apps across enterprises, we are tied into specific clients and frameworks that are part and built for that language. And we have to maintain these apps on an app-by-app basis. The platform engineering teams are usually on the hook for the application platform layer here. That's all of the authentication, observability, maybe even artifact registry, secrets, common storage layer, messaging, and more types of capabilities. And for the application platform team to be able to evolve their platform, if they are trying to make a new API level change, moving to a new major version, application developers have to update their dependencies, but they're not just revving for being able to evolve the platform. They're revving because most of our application code is not our code. It's full of open source code, which is actually a great thing. It's amazing that we're able to do this. However, that comes with a significant cost and burden on maintaining your application code to prevent vulnerabilities. And so both by having boilerplate code for your platform and for open source dependencies, we're constantly churning on this application like hamster wheel of building apps. And we don't really have an easy way to wrangle that problem. And now on the running and deployment side, platform engineering teams are stuck managing these very expensive platforms. Typically, it's built on top of Kubernetes today as the orchestration layer, and it really lacks portability, because it doesn't allow us to run in many different types of environments like on the edge. So throughout this platform evolution that we've seen, moving through the public era, including containers as part of that era, but that being the major paradigm shift, I believe that today we are now in a new componentization era, where our new next unit of compute is WebAssembly components, and that's orchestrated by wasmCloud. So let's take a step back and just do kind of a basic comparison between WASM and containers. You can think of WASM as perhaps a tiny VM, so this type of direct comparison works okay. Containers themselves are much larger. They're usually in the order of megabytes to gigabytes, whereas a WebAssembly component is in kilobytes or megabytes. WebAssembly components themselves are secure by default. For containers, we have to add a number of processes, best practices, and tools to get them to a place where they are secure and provide the right level of isolation. But they're still not generally considered the right choice when you're trying to run arbitrary user code, and certainly not on a user's device. Now, the other difference here, while containers give us much more new layers of portability, those images are still CPU architecture bound. Whereas WebAssembly components, this .wasm, it doesn't need to change for any different environment, so long as that environment has a WebAssembly runtime for it. But perhaps the most important difference between containers and components is that containers start in seconds, whereas WebAssembly components start in less than a millisecond. And that really enables WebAssembly components to solve this major problem that we have in the industry, is that it solves the cold start problem. Containers, because they take several seconds to start, they have to keep effectively a pilot light on. They have to keep many different containers running, even though they're not necessarily servicing any requests, because when you get a burst of requests, it takes seconds to scale out. And your response time that a typical user expects is less than a second, so you can't wait on a new container to spin up. Compare that with a WebAssembly component. This list of numbers here, these are numbers that every programmer should know. You've probably seen this set of numbers before, but I think it's really important to highlight where WebAssembly components fit into this latency story. WebAssembly components, because they start in less than a millisecond, it means that it's so much faster than even making a network request. And so you're going to see new types of architectures evolve because of this new layer that WebAssembly components fit in. Why make a network request to somewhere else when you can be running that compute on the edge next to the user? Now, with every new unit of compute, every new thing that we're distributing around, you need a new orchestration layer for that. And that's what wasmCloud is. It's a WASM native orchestration. It allows you to deploy and manage your WASM applications across any device, cloud, or edge, including your own. Now, when we're building a WebAssembly component, you get a new way of simplifying the way that developers need to build, because you're able to reuse your logic with essentially composable building blocks. And that lets you eliminate boilerplate from your code. It lets platform engineers build a component that slots in, that the application developer themselves don't have to manage. And one thing I really want to highlight here is that WASM native also works with cloud native. It has all of the existing cloud native technology integrations that you would expect. A common deployment strategy for wasmCloud actually is to be able to run on Kubernetes and orchestrate your applications with wasmCloud. When we compose applications, we're doing that in wasmCloud with open standards and common interfaces for platform capabilities. These can be swapped at runtime, allowing you to do upgrades for maintenance or even changing out the vendor entirely, because these APIs are at a high level. They're vendor agnostic. Now, we also allow you to write your own custom capabilities and interfaces, and we've had an amazing amount of success, and we'll be doing later deep dives on our integrations with Postgres and Couchbase. One thing to understand when we're talking about building apps for wasmCloud is that we have a declarative application manifest. You might later today hear the word WDAM. That's what we're talking about there, the WebAssembly Application Deployment Manifest. And you can just think of that as like a Docker compose, but for WASM. When we run WebAssembly applications, aka we're running them in a deployment, we allow you to run that across any device, server, or cloud. Now, this is something that's very, very different from other types of application architectures. It allows you to have a seamless distributed network that automatically load balances and fails over to available compute. We support vertical and horizontal auto-scaling with automatic failover, allowing you to reach this new level of reliability and fault-tolerant applications. Another added benefit here is that we do all of this routing local first. So if you're working in one region and there is a type of capability that's closer to you, we route to that first before reaching over across a different region. So in this scenario, we're talking about orchestrating WASM applications. You know that Kubernetes is a container orchestrator, so you can at least think of wasmCloud as Kubernetes, but for WASM. Another major feature of wasmCloud is that it's extendable at runtime. This is effectively a view of our stack for wasmCloud, where we support WebAssembly components that run in a WASM sandbox. We have our WASM host, which embeds a WebAssembly runtime called wasmTime. And then we have many different capability providers that are extendable at runtime. A single WebAssembly component has things that are called imports and exports. These are basically APIs. For imports, these are the things that my component needs to run, and my export are the things that my component provides. So in this case, I may be getting many different secure capabilities that are built into my host. These are often the WASI APIs that you see. And I can also import from extendable capabilities that can be swapped at runtime. Another amazing feature is that WebAssembly components themselves can build on top of each other, just like Lego blocks. And in this case, I can have one component who imports, aka depends on another component that exports an interface that it needs to run. So you might be thinking, why components? We already have containers. We have had amazing success with containers. So why do we need to go back to the drawing board on our fundamental piece of compute? And really, I think that part of the problem is the way that we manage with containers. We're bringing in the whole world. Whereas with WebAssembly components, we get down to exactly your business logic that is bundled into the app. And when we start back from first principles, we know that we need to use applications that are written in many different languages. We need to be able to support polyglot. And so we're able to do that with WebAssembly components, where one component written in Rust and another component written in Go can compose together and communicate over interfaces that are designed so that we can do interface-driven development. And they are also shared nothing linking, so each component is actually still isolated from each other. Now, you would think that with this level of isolation, there would be this massive performance cost, but that's really not the case. Going back to our latency numbers, now imagine two components that are composed together. In that case, they're actually able to run in the same process, which means when I communicate across that boundary, it happens in nanoseconds. And that is a major difference in game changer. Now, the way that we define these interfaces is with an IDL called WIT. It gives us some new capabilities that we don't have in OpenAPI or other IDL type technologies. And that really comes down to the interface types that we get out of the WebAssembly component model. And that is namely things like resources and streams. That gives us the ability to manage the lifetime and lifecycle of components as they're composed together, and in wasmCloud as they're distributed over the network. Later on, Brooks Townsend is going to give a deep dive on how we're able to use resources in a way that solves privacy and security concerns with our secrets. But more than anything, by using WebAssembly components as our primary unit of compute, we can see emerging types of patterns that are going to help platform engineering teams solve major problems that they're experiencing today. And I believe it's with the platform harness pattern. We're seeing that across many different enterprises that are adopting wasmCloud, where essentially they're building a golden template that all of their applications are able to compose with so that they create a single component that isolates and I would say wraps effectively all of the different logic that they need to be able to get their authentication, their secrets, all of the basic things that platform engineering teams are on the hook to provide, but they have the benefit of managing that themselves and maintaining a lifecycle separate from the application developers component that just composes their app. And once this application component is composed together, you can see that it doesn't expose those imports. It can now just run with the basic standard APIs. So what that gets us to is composable computing that can be distributed across the core and the data center, across edges and clouds. And that's going to be very powerful change in our industry. So to give you a taste of the art of possible, I'm going to give you a demonstration of a celestial and terrestrial mesh. Now, this is something that we are building in partnership with a number of different agencies that are interested in running WebAssembly in space. What I'm showing here on the screen is a world map with different data centers deployed in Azure and their connectivity over the internet. The job of this application is to identify whether or not something is a boat. So it's doing image classification once I upload an image. Imagine some satellite has just taken this photo and I need to image classify whether or not this was actually a ship. In this case, it decided that it was not a ship, so my prompt engineering here isn't amazing. It's pretty simple. Okay, this one is a ship. Let's do something else. Let's go right back up. Let me give it something that is definitely not a ship. And this is a member of our team. His name's Oscar. And he is not a boat. That is Oscar. And we'll do just one more boat before we're done, just so I can know that here's a boat. That one's actually an AI-generated boat, but it's real enough for an image classification system, exactly. So we'll dive a little bit more into the different pieces and parts that make this app real from the different capability providers as part of it, but I wanted to go ahead and introduce you to the use case. Now, this is a different view of showing essentially that global view that I showed a second ago, where we have a distributed compute mesh. And the use cases for this that we're seeing is actively growing. And today's methodologies just can't achieve it. Kubernetes itself and containers are not well suited for running in embedded devices on the edge, whereas WebAssembly is fantastic for that use case. And composing all of this together with the right enterprise-ready security and compliance controls, it makes wasmCloud ready for organizations to adopt. Now, you might be thinking this is new to you, but I just want you to let you know that this technology has actually already won. We're seeing it from Fastly and Cloudflare for serverless edge computing. It's in your TV. It's probably in my camera right now. It is definitely in Zoom that we're running. It is the way that we distribute our videos from Prime Video, Disney Plus, etc. It is taking over the cloud native landscape by storm as being the last plugin model that you'll ever need. So that means that WASM has taken over the industry and you're using it everywhere. The future is here, it's just not evenly distributed. So I hope today you'll learn how wasmCloud is the picks and shovels that you need to bring WASM into your enterprise. Thank you. So we are actually going to dive into the really good stuff, which is actually the technology. And we're going to have a number of technical deep dives back to back. And the first one up is Brooks Townsend, and he is going to discuss how to do secrets, pluggable secrets with wasmCloud.
Hey, yeah, thanks, Bailey. So I am going to walk through, as Bailey mentioned, we're going to have a series of deep dives into the latest innovations in wasmCloud, especially since we hit 1.0. And I have the pleasure of walking through the most requested feature on our wasmCloud roadmap during our community planning session for earlier this year, wasmCloud application secret support. Specifically, wasmCloud applications needed to be able to fetch and use secrets at runtime that are encrypted in transit and at rest. And as we proposed the design of secrets, it was critical that we approached adding secrets as an extendable layer and not tightly couple wasmCloud to any particular solution. It was also important to design this in a components native way with a standard interface so that it can be used in any language that supports WebAssembly components. We knew that we would provide an API as a collection of functions and types that developers could import into their code and write business logic in terms of secrets. Of course, this would also need to work just as globally distributed as wasmCloud does. So what is our solution? We designed the wasmCloud Secrets WebAssembly interface, the Pluggable Secrets API over NATS, and we started implementing secrets backends or reference implementations. At the same time, we pushed updates to our application specification, WADM, and command line tools to support managing secrets in wasmCloud apps. On the right, you can see an example application. This is how it actually works today in a wasmCloud app that uses a policy to instruct wasmCloud how it can pull a secret at runtime, and then how the secret is specified in Vault down at the level of a component. So I want to show a couple of diagrams and talk through how this actually works in the wasmCloud ecosystem. So at runtime, wasmCloud is responsible for orchestrating WebAssembly components, and capability providers are also called native plugins. Secrets is actually a built-in host plugin that's configured as soon as wasmCloud starts and immediately is ready to support multiple secrets backends based on what applications declare in their manifest. Secrets backends are responsible for encrypting and storing the secret, which we know current secret solutions like cloud provider specific key stores or HashiCorp Vault are very good at. And wasmCloud is responsible for making sure that all secrets are encrypted in transit as they're fetched from the backend. Now we use NATS X keys for this, which are elliptic curve key pairs that provide strong cryptography and are actually very inexpensive to generate on the fly at runtime. So supporting this NATS API, which is how this secret solution is extendable and pluggable for wasmCloud and how we don't tightly couple to a particular solution, is using the NATS API. And supporting this is very simple. You supply a subject to wasmCloud when the host starts, and then your backend pluggable layer just needs to support two endpoints. The first one is just a request for the public key that the server is going to use to encrypt secrets in transit. And this is just returning the actual key that the backend is going to use. And the second and important one is an endpoint called get, which is used to send the context of an entire secret request. So what secret needs to be fetched, what component is fetching it, what host is fetching it, what application the component belongs to. And then the backend can make a decision based on that or based on an external policy to return the secret or an error response. Now, this is, of course, going to be encrypted in transit. And every single time that this get function is invoked, we generate a unique request X key, which prevents replay attacks, even if the NATS network itself for wasmCloud was compromised. Now, it's very important to know here that all secret fetching in wasmCloud is facilitated by the host itself. No components or capability providers actually fetch secrets on their own. They're just handed secret values. So this actually works a little bit differently for providers and components. So let's go through both scenarios. So you have an application that specifies a capability provider and it requires a secret. And Wadum tells wasmCloud to start the capability provider as a part of deploying your application. So wasmCloud sees the specification that you've laid out for the secret, and it will send a request to the secrets backend that you have configured with the context of the provider and the application that's requesting it. The backend then will analyze that request and then allow the secret to be sent back encrypted over NATs. And then the host will actually start the provider along with two opposite pairs, two opposite pieces of a key pair. The provider receives the host public key and its own private key to use for secret decryption. And the host stores the host private key and the provider's public key for encryption later. So this ensures that this individual capability provider and only this instance of the provider can decrypt secrets sent by the host. If the provider or host is restarted, those keys are completely discarded and generated new if it starts again. So I included a little code sample here at the bottom, and this is almost exactly the line of code that we have in our host to do this encryption. But using the private key from the host, you can then seal or encrypt a secret value and specifically target that for a recipient, which is the provider's public key. So this is a very nice asymmetric encryption algorithm. Now, for components, this is a little bit different, but most of the entire process for fetching secrets is exactly the same. So when the component starts, if there's a dependency on a secret or the component specifies a secret, wasmCloud will request the secret from the backend. And then, since components are running alongside the host and there is no need to transmit that secret over the wire, we actually just cache that in memory with the secrecy crate, which ensures that the secret is zeroed out from memory as soon as the component stops. And then the component itself is able to access these secrets at runtime with the wasmCloud secrets interface. And the wasmCloud secrets interface, the two functions get and reveal, are actually built into the host. This is a built-in plugin. This is a key piece of innovation of the secret solution, not just making sure that we have encryption and decryption handled correctly, is the secrets WIT interface. This was meticulously designed. We collaborated with several folks in our community and champions within Waziland on the final design of this interface. And the end result is something that's really simple to use, but has a very key piece, a very key WebAssembly innovation that makes it special. The secret itself is initially fetched with the get function as a resource, which is actually an opaque pointer to the actual secret value. So when the component calls get, we don't actually load that secret into the component's memory. You can pass that secret around with other WIT interfaces that are designed with this secret type. So you can pass a secret from component to component, from component to provider, without ever revealing that value in memory. And then finally, secrets are actually entirely encrypted the entire way in transit and at rest, all the way up until a component or a provider reveals it. Now, this implication here around the usability is nice, but the real huge benefit is for platform teams, especially at enterprises where secrets need to be part of applications that aren't just like API keys or a token or a password, but they're sensitive data that should only be revealed under very strict circumstances. Customer data, PII, HIPAA data, payment information, all of that can now be sent all the way through a chain of applications without ever being revealed so that you can process that without seeing the secret itself, without ever actually loading the secret into memory. It's very impressive. I'm very proud of this part. Now, this was again, we designed this with other members of the WASI community, and the hope is to contribute this upstream as a WASI secrets interface as a phase one proposal as soon as we can. And all in all, you can see my excitement boiling over. I am incredibly proud of the secrets implementation and what our maintainers and community contributors were able to put together for this implementation for wasmCloud. And I'm very excited to see all the use cases and these implementations come to life. If you are interested in using secrets in a wasmCloud app, please check out our secrets documentation. The link is up at the top. But if you just go to wasmcloud.com and search for secrets, then there is great information about how to import the WIT, how to add secrets to your custom providers, and how to connect to your own secrets backend. So that is all that I have for the deep dive into secrets. Anybody watching, if you're on YouTube or in the webinar itself, please feel free to put in questions in the Q&A and I can get to them as I come off here. For now, though, I am going to go ahead and hand off to Lucas Fontes on our team, who's going to be talking about the evolution and innovation that we have been doing in Golang. And there's been a lot in this area over the past couple of weeks, especially, that all kind of culminates from the efforts that have been happening in the ecosystem, in the wasmCloud world for components, in the TinyGo implementation for WebAssembly, and more.
Hey Brooks, before you go, what if I were using somebody like CyberArk or another secrets provider? Would it be possible? Is it compatible with the design, even if it's not supported today?
Yes, absolutely. So let me, sorry, Lucas, I'm going to steal back from you for a second. A very important part of this design for wasmCloud Secrets was not tying to a particular solution. On this screen, we have NATS key value, which is one of our reference implementations. We have HashiCorp Vault. Lucas actually implemented the implementation for Kubernetes secrets and bringing those into wasmCloud. But this API is pluggable and very flexible for a reason. So if you have something like CyberArk or AWS secrets manager that you want to bring in secrets from and you don't want to store them in a different store, the implementation of a secrets backend is very simple.
Okay, thanks, Brooks. That's neat.
Yeah, great question, Liam. Okay, Lucas, I think I can I'll relinquish to you for real this time.
Sounds good, and thank you. Hi, everyone. My name is Lucas Fontes. I'm an engineer here with the Cosmonic team, working on wasmCloud and focused on infrastructure, Golang, a bit of the framework story there. And today I want to talk a bit about the evolution of Golang and Wasm together. And what I'm going to cover here has to do with providers and also components. This is how you create your providers and components using Go and integrating that with wasmCloud. So pretty much these two boxes here. The story between WASI and Golang started about a year and a half ago with the first inception of with bindgen. And what this was, it gets your with interface, all your types, and generates Go code so you can write your servers, your microservices, and things like that using just vanilla Go. But the challenge with that approach is you're always generating C code to go together with your Go code. It was a way to get started in the ecosystem, but we knew from the beginning it was not sustainable. Around August 23, TinyGo, which is another Go runtime focused on smaller environments and embedded systems, it implemented what we call the WASI Preview 1 spec. And the WASI Preview 1 spec was first landing in TinyGo with a fast-forward landing in Big Go in September 23. And this was great. This was the first time that we were able to get components in Go running inside a WebAssembly runtime. That was nice. But then come around February 24, we saw that WASI was evolving, and then we saw the WASI Preview 2 being born. Around that time, we had to get Go, literally, running with WASI P2. And in order to do that, we focused on TinyGo implementation, as getting that inside TinyGo is easier than getting that in Big Go. It moves faster, the community is responsive, the developers are awesome. And with that, we got WASI Preview 2, which was a change in the underlying implementation of how those binaries are generated in TinyGo, which gave us the opportunity to implement a with bind gen Go that got rid of all that C code, which was problematic at the beginning. And in July 24, we were able to release the provider SDK, which allows you to generate your capability providers in wasmCloud, and also the with bind gen Go, which generates your with interfaces in Go without any C code. Right after, in August 24, about a month later, we had the Kubernetes secret provider also being implemented in Go. This came with the realization that the Go libraries for Kubernetes are pretty much Kubernetes is built on top of Go. So it was a pretty good story, pretty good implementation story there. And with this, we had the initial implementation of secrets backends in NAT, using NATs with Rust, and the Kubernetes one in Go. This also proves that we can be using any languages here to provide to create the providers, components, and also the secrets. Now, here in September 24, we want to talk about a component SDK and also about West, which is how you test your components in Go. And why do we need an SDK here? The initial code gen that I was talking about that generates Go and C code generates the types, the structs, the functions they are very verbose. And this is calling into C APIs and is very low level. And in reality, what we want to do is write Go code that is more idiomatic. You want to write an HTTP server with a handler. You want a round tripper. You don't want to be calling inside WASI interfaces all the time. So the component SDK is abstracting this communication and giving you standard library constructs that you are familiar with. On the left here, you can see the code that was generated with the initial bind gen. And on the right, we're seeing what is possible once we have the code gen in Go and also the component SDK. It's essentially a regular web server in Go. And Brooks approves, which is a good thing. Why an SDK? We are doing here is providing abstractions on top of WASI and converting that to the standard library. It's completely optional, and you don't need to use it if you don't want to. But we highly recommend it so you can get started quicker and also use a bit more of your usual tools. For example, we do have WASI logging, but in Go, you're used to writing your logs using slog. So what we have is an slog adapter that once you use it, it uses WASI login underneath. And I want to just show here how these components look like in a mini demo. And we're calling it the Large WASM Collider. And sorry to disappoint everybody, this is not the Large Hadron Collider, but we will also make some packets bump into each other here. On the top right, we have kind of a view of the real Large Hadron Collider. And what is going on there is you have a control room, a control center, injecting a particle into loops. And those particles will be looping inside this large ring. So what we have in here using wasmCloud is 5 wasmCloud hosts, where one of them is a control room, and it injects a packet, a particle, inside the system. And this is all using components. Once we inject a particle into the system, it's going to be looping in one of those 2 arrows, either through a regular path or through a special path. The interesting thing here is there is no actual RPC code telling it go to this IP or go to this port or encode use JSON or gRPC. You are literally programming as if you were interacting with a library, but your calls are being sent to a remote host, and you don't need to do anything for that to happen. You get free instrumentation and observability of your system with that. So I'm gonna swap here quickly. How does this look like? Again, we're injecting packets here and things will be looping. We have 2 routes, one that is the default, one that is the special. And once we inject packets, we want to know in each one of these points for how long the packet has been going around the system. And in here we see each one of those packets that are being injected with their defined ID, how long they took to go through each one of those hops, how many of those calls are failing, are succeeding, latency, logs. All these things are being given to you by the platform just by writing your basic HTTP server or component. And to take a look at how that actually looks like, this is the entire code for the system that simulates this Large Hadron Collider. We have a blast handler here, which is a regular HTTP handler. We receive a request in JSON. We parse the request as if any other regular HTTP request. And we also introduce some chaos in the system. And what this means is we want to make the component panic and just simulate a failure there to see how wasmCloud will react to that failure. Once we do that, we generate a packet ID, and we inject that into the system. And we tell this packet, just go start your looping. And we return back a JSON response to the client. The difference you will see here is instead of using main to write your program, you will use init to bind your HTTP handler to the WASI HTTP interface. And this is where we are bridging those 2 worlds. And likewise, the probe itself, each one of those points in here, the blue ones, what they need to do is they need to forward packets. They receive and forward packets. How do they look like? Again, they are regular Go functions. And we first see if we have a special route. If we do, we take the special route. We then check when the delta between when the packet was created to the packet received in this probe. And then we call the logger. And you can see here that we're calling a logger here that is slog, literally, but this is being fulfilled by wasm logging. If this is the last time that we should see this packet, we pretty much just bail right here. Otherwise, we do one of my favorite features of wasmCloud, which is component linking at runtime. In here, what we're doing is based on the route, we might send this next call of the packet looper interface to either host A or host B, depending on the route that was picked. And this is configured using wasm based on a link name. What we're saying here is, hey, wasmCloud, next time I call the LWC packet looper interface, I want you to point it to a specific location, which is going to be this target route right here. And then we just send the packet to the next hop. Right after that, we do a bit of checking for the random. And if it's kind of we're within the bounds of the random number, we panic right there. And again, in the init function, we say, this is the function that is fulfilling the with interface. And calling this, I have this running here in the background, but just to show you how this kind of looks like, and don't want to spend too much time here. We pass here how many times we want the package to loop into the system in the TTL, time to live, how percentage of chaos to introduce in the system, and which path to take. And once we do that, we receive back a message with the packet ID, which route it's going to take, and pretty much the things that you provided in the request. If we go back here and all the way to the bottom, we should see that 542 is this packet. And I really want to see if I can expand this so we can actually see the 542. There you go. And this is how long the packet took to kind of go 1,000 times around the system. Why is this interesting? Here we can see how much latency wasmCloud is introducing, the different aspects of failure scenarios, what happens when things break. The information that you see here is coming through OpenTelemetry. And as you saw in the code, there was pretty much no mention of OpenTelemetry in the whole setup. The next thing that I want to talk about here quickly is about WEST and component testing. WEST is a testing framework for WebAssembly components written in Go. And the challenging testing components is that your laptop, your Mac, your Windows laptop, it's not an actual WASM runtime. So you're not going to have the WASI logging, WASI HTTP, WASI core interfaces available to you there. So what you need to do is compile your code and then run that inside wasmtime. If in writing tests, you want to be able to stub interfaces and provide some different messages, some different errors, so you can make sure that you have proper coverage. And the trick here is if you using Go test, if you simply run Go test on top of a component, it will tell you that it doesn't know anything about those interfaces because those interfaces are not in your system. When we run this test with WEST, we can mock those calls to WASI logging and pretty much return anything that we want back from those calls. We can check the parameters that you received. We can send a different response. And we can also simply pass through the WASM runtime. What WEST is doing underneath is actually instantiating a WASM runtime, wasmtime, which is the one that powers wasmCloud, and linking your Go code to the component code in each one of your tests. And to write this is pretty simple. You don't need anything special other than including the WEST library in your code. I'm not going to spend too much time on this one because it's a pretty cool one, and there's a blog post coming up soon. So just to recap here, with BindGen Go is the way to generate with interfaces in Go, and the component SDK bridges the gap here between the complexity of WASI streams, WASI HTTP, and brings that into Go native libraries. If you're writing components targeting WASI Preview 2, TinyGo 033 and above is what you want to be using. Is in terms of the larger Go community, like the big Go as we call, that support is still coming. And you can follow up on those two PR links that I have here. And this is to say that in wasmCloud, you can write providers and components in Go in a very idiomatic way. It's not going to look like you writing C++ in Go or anything like that. The capability provider is for when you want to run long-running processes, you want to have more state. And the component SDK is for when you're writing components, things that are functional and supposed to be stateless and short-lived. And that's all I have here for Go. Thank you.
Hey, Lucas, this was awesome. I had a quick question. I hope you don't mind to interrupt before the next session. So I can see that like the code that you showed in Go looked really nice. There's the init function and then everything looked really nice and idiomatic. But before, like when I was using I was using wit bindgen generated types directly, and I thought that's how that worked with a component. So like how does this SDK work with compiling to a component?
That's a great question. So what the component SDK is doing is generating those with interfaces at the component, at the component SDK level. So we pre-generate those interfaces, and we have abstractions on top of it to be a bit more direct. What's going on there? I'm not going to make it a little bit bigger. Is the component SDK itself has a wit. And the component says, I can fulfill all of these interfaces here for you. So if a component wants to use one of these interfaces, it can do that. And back here to the probe example that we had, what the probe is saying is bring in the wasmCloud component imports. And at this point, you can start using all those interfaces. The part that is interesting here is you see that we do provide abstractions for HTTP. But that doesn't mean this gets hidden from you, taken away from you. You still have to declare here that you have this incoming handler, that your component is responsible for this incoming handler, even though it's being fulfilled by the component SDK. Why is this important? Tomorrow, you change your mind. You don't want to use the component SDK anymore. You get rid of this, and you pretty much detach from the SDK altogether.
Okay, really cool. Thanks for bringing up that repo too. I tried to send that out across all the channels so that everybody could take a look there too. Well, I didn't see anything in the Q&A across our stuff, so I think you're good to go on to wasmCloud Operator.
Cool. Hi, everyone. I'm Lucas Pontes, and I'm going to be talking here quickly about the wasmCloud Operator. And this is the story for the platform teams and leading a bit of the development land and going to operations a bit. So up until now, we've been talking a lot about WASH in terms of components and capability providers development. And the usual flow is once you have your component built, once you have your provider built, you're going to push that code up to Git. That's going to go through a CI pipeline and generate an OCI image of your component or provider. From this point on, another group in your organization, the platform team, will get that code and is responsible for getting that code and putting that in production in your public cloud, bare metal, anywhere. And this group is more familiar with like a different set of tools. And the wasmCloud Operator is tailored to help the life of those folks. They are dealing with kubectl, they are dealing with Jenkins, they are dealing with a different set of systems that developers might not be exposed all the time. what the wasmCloud operator does is it facilitates the setup of a lot of the infrastructure and applications, helping the lives of operators and again, making sure that wasmCloud is adhering to the industry standards that most companies are familiar with. So what does it do? It allows us to create groups of wasmCloud hosts and also deploy application manifests. I'll show you in a bit here how these look like. But for right now, just think that these is pretty much YAML that we're talking about. The other thing that the operator does is as you expose capability providers in terms of TCP ports from wasmCloud, those need to be reflected in Kubernetes so they can be exposed using load balancers, ingress interfaces, and other things. The wasmCloud operator is watching your deployments in wasmCloud and making sure that these are also being exposed on the Kubernetes side. And the third thing is integration into Kubernetes secrets. This is a good one because you need secrets at some point in your application. You don't want to be putting your secrets in a YAML file, putting that in Git, and calling it a day. The interesting thing with the secrets integration here is because we're integrating into Kubernetes secrets, you can bring in an external operator like the external secrets operator and plug into many different endpoints. AWS Secrets Manager, Google, Vault, you name it. And the repository for the operator is under wasmCloud operator. And host groups. Host groups are pretty much the wasmCloud runtime itself. When you run wasmCloud, when you run wash up in your laptop, you're bringing up a single wasmCloud host. What the CRD here is doing is you tell it which version, which lattice, and how many you want. And it will take care of creating the deployment and also enforcing some good patterns in standing up wasmCloud hosts. So every time you bring up one wasmCloud host, we make sure there's a companion NATS leaf node right beside it, so it can have faster communication with NATS. It's also responsible for making sure that the configuration traverses from your YAMLs down to Kubernetes deployments into the actual pod, and also the communication on the other direction. Is this pod healthy? How many applications do I have deployed in each host? Do I need to recycle them? How do I upgrade them? So the status reporting here is also an important part. The other thing that is interesting is because now you have this being declarative, and you can use any tools that you already have in your DevOps arsenal. If you have Argo, if you have Flux, if you have kubeconform to check if your YAML is in check, these things are all possible. And as Bailey previously mentioned, WADAM is our application orchestrator. And the manifest there looks suspiciously like Kubernetes. And this is not by mistake. What we're doing there is we're using a spec called Open Application Model, which is rooted in Kubernetes, making this a very good match that you can, in your local development, use wash app deploy to deploy an application to your local wasmCloud environment. And the operators can use kubectl apply on the exact same file and get this to work once the operator is there. In this manifest here is where you're going to declare your components, your providers, your links. Everything that you want on your application goes inside this file. The other thing that the operator is doing is the service reflection that I mentioned initially. And this is done in a way that we keep the life cycle of the service being exposed in sync with what is happening inside wasmCloud host. What this means is we set up a finalizer on those services to make sure that they don't simply go away by themselves. So if they get deleted, the wasmCloud operator gets a chance to go in there and maybe recreate it, maybe update it, you name it. The life cycle here is also important because if you bring up more wasmCloud hosts to your system and you start positioning, you start spreading providers that existed into these new hosts, the operator will also include these new hosts into your service, into your endpoint slice. And the other bit is about the secrets integration that I mentioned initially. The important thing here when bringing secrets to Kubernetes, wasmCloud secrets to Kubernetes, is we need to make sure that we are playing nice in the Kubernetes ecosystem. We need to respect service accounts. We need to respect RBAC namespaces. And this is done through the concept of policies. In here, we want a wasmCloud secret called API key, and we want to fetch it from the Kubernetes default policy defined up there. We want to get the secret called app secrets, and inside that secret, we want to get the secret key API key. So you can imagine that this might live in the same namespace or in a different one, and you can configure those things here through the policy just by adding service account or default namespace in the property section. And now I'm going to do a kind of a quick demo here, which is going to show a bit of the senior YAML engineer chops. What I have is, oh, right, quick start, nice. What I have here is a Kubernetes cluster, which already has the operator installed. And I want to bring up a wasmCloud host and also deploy one application. Let's see how many pods we have going on. So we just have Nats with them and an Alpine container that I was playing initially. In terms of YAMLs, we have a wasmCloud host config YAML, and this is going to bring up one wasmCloud host in the 1.04 version in the lattice default. And you notice that I didn't specify the number of hosts. If you don't specify the number of hosts, the default is 1, kind of to show that we also have some same defaults underneath the system. Getting the host there. Once we apply this, we're already creating a deployment and a pod for wasmCloud host. And from this point on, we can describe that and see all the properties of that specific wasmCloud host. We don't have any applications deployed there. It's connected to NATS, the version, and everything. For my application, what I have here is a basic Hello World application, which is coming with one Hello World component and one HTTP provider that's going to be binding it to port 8080. And once again, I can do this with kubectl apply. Now, the interesting thing here is I can do the kubectl approach to show that this application is deployed, or I can use wash still. So these things are working in sync. When we request information from Kubernetes, what is actually happening is Kubernetes is going over to wasmCloud host, asking how many applications are there, and coming back. This is to say that we implemented the operator here as an API service. This means that doesn't matter if you apply your applications using wash and check them via kubectl or vice versa, the system will be consistent. There is no way for somebody to install an application using wash that the operators will not be aware of. And once we apply this application here, we also see that now we have a Hello World service here on port 8080. Again, this is that service reflection that I was talking about a few minutes ago. This is all great. And where can I see this that you just showed? There is a quick start, which is literally this thing that I went through here. It shows you how to install the operator, get NATS with them, and also the bringing up a wasmCloud host and a sample application right beside it. in terms of future work, we know that the installation story right now is not the best. This is because you have to install NATs with them, the operator, and they each one have their own installation procedures. So there is some Helm installing that goes in there that requires a bit more love. We have a member of the community working on a Helm chart that will encompass that and make it so the Kubernetes story comes in a single Helm chart in a way that things are way easier to install. We also want to look into the gateway API integration so we can plug wasmCloud easily into Envoy, into Nginx, and other Ingress classes. The other part that it's coming up soon is the ability to create end-to-end clusters. You might want to create multiple wasmCloud clusters inside a single Kubernetes cluster, or you might want to create one wasmCloud cluster that spans multiple Kubernetes clusters. So these things are important in the day-to-day for any company at this point, and we want to make sure that we are supporting those use cases as well. And that's the end of the operator chat. Once again, thank you.
Hey, Lucas, me again with another question.
Hi, Brooks.
Yeah, hey. I had a question. So I think I understand the wasmCloud operator, but I think that the separation or the distinction of like where should I run and like should I run an application in wasmCloud? Should I run the application on Kubernetes like with why I am today, with like the way that I'm doing it today? And I think a lot of people would be surprised to see that we're deploying wasmCloud on Kubernetes. Can you talk a little bit about like what the benefit is here for an operator like us running WebAssembly with the wasmCloud orchestrator and then like deploying our platform with a different orchestrator?
Sure thing. wasmCloud itself is in the pillar of infrastructure. You can see it as a separate layer. So you have right close to the metal, the actual hardware, you have the operating system, you have containers, and right up until components came around, we were allowing all developers to have the same level of access that like an operator root security teams would have. The fact that we're deploying wasmCloud on top of Kubernetes means that we now have another layer, and this layer is responsible for components. So in this layer, operators have way more fine-grained control over what they are allowing the containers to do. So where previously you allow somebody to deploy a container and they can shell out, they can open TCP connections, they can poke around in the cluster. With components, it's a deny by default, and you allow them to do specific things. The key point here is wasmCloud is Kubernetes for components for WASM, but it can also run in isolation somewhere else. We can take wasmCloud, run that in bare metal. We can run that in satellites. And you can imagine a situation where you have your Kubernetes cluster in US East 1, like many people do. And you also have your data center with just 3-4 servers. And you want to see that communication happening as a single flat network. So you can deploy a component and say, I want this component to be running only on my data center, or I want this component to be running only on my Kubernetes cluster. And this, I think, the interesting concept here of seeing wasmCloud more as a layer on top of your existing infrastructure.
It makes sense. Really cool.
Awesome. Thanks, and I'll hand it off to you, Brooks.
Yeah, sure. So now we are going to just keep on schedule here. We're going to move on to Wash Dev with Victor. So this is going to be talking about essentially a new proposal that we have been working on over the past couple of weeks for washdev v2. And this was an RFC that got a lot of positive attention in the community. And I'm really excited to see, I've seen the individual PRs come across, but I'm really excited to see what Victor's put together here. So, Victor, whenever you're ready, go ahead and take it. And maybe introduce yourself. I didn't even do that in the beginning, which is my bad.
No worries. Hey, everybody. I'm Victor. I work as an engineer here at Cosmonic, and we've been focusing lately on washdev and trying to get it, really tight and to increase and improve the onboarding experience and the developer experience. Because obviously, if we believe in a world where people build WebAssembly components, people use providers to abstract dependencies and plug and play and really get all that going, we need to make sure that interface and that developer experience is really, really tight and sort of a tight feedback loop. So washdev is something we've actually had out for a while, and we are improving it and trying to really dial it in. So here, let me share my screen here. Everyone should be able to see this. So as I've said, washdev is for building wasmCloud projects. Components, and when we say wasmCloud project, just to make it really clear, we mean both WebAssembly components and capability providers. We use the word app because it's sort of an app involves more than just one component, right? You've got a WebAssembly component, you've got a provider, let's say an HTTP server, and a handler for that HTTP endpoint. So just to set level set a little bit here, when we talk about a project, we can talk about either WebAssembly component, which you might think of like an app, or one of the infrastructure dependencies, right? Those middle pieces that we're helping you abstract away from, which are capability providers. So washdev, one of the things that we thought was really important to get the developer experience right, level 0 is just building, watching your source code change, rebuilding, and redeploying, right? But what we wanted to do was to leverage some of the WebAssembly interface types, and we've up until now we've called that WIT, right? And so we wanted to use that interface language, that IDL, to automatically pull out your dependencies based on what you're importing and what you're using. Now, you can think of this pretty simply in that if we see you're building a component, let's say you're building a component that handles an HTTP request, and you have an import, or you have an import of, let's say, key value, right? And so we know that this component must answer an HTTP request, and it must use some sort of key value capability provider, right? Whether it doesn't matter what the key value store is, right? It could be Redis, could be Couchbase, could be lots of things, but we can tell those things just from the interface. Now we can take that interface and we can use that to generate automatically the spec as sort of a local mock of the deployment environment and deploy it locally, right? As opposed to just deploying just the one program, right? And so we've really leaned into that and tried to focus on that for both imports and exports. And this is for capabilities that we consider really important and vital, sort of baseline capabilities. Key value is one of them. HTTP servers are one of them. Outgoing HTTP requests is another one. There are a bunch, and we're always open to expanding this in the future as we see usage go up for certain interfaces. But the core of washdev now, as opposed to before, is build your component, watch your code, build your component, deploy your component locally, and spin up its dependencies where we can. So here's just a quick look, and I'm going to demo it really quick here on what the output of this looks like, right? And it's what you'd expect, right? We sort of go through, we sort of generate you a session, because it turns out you can run more than one command on a computer at the same time. So you could have 2 washdev sessions running on the same machine, and we want those to not collide. And you can have the component get built, right? And or provider, right? You can also get an HTTP server built, spun up. So we have our managed and sort of officially supported capability providers, and HTTP server is one of them. As such, we know that we can, since we know that provider well, we can spin it up actually for you, automatically give you a place, and you can see it sort of here to the bottom, the third line from the bottom here, that we can give your we can figure out the address that the HTTP server is running at and tell you where to go hit. So you can sort of, while you're testing, you can just open up a web console, a web browser, and take a look at what your component is outputting. So I'm going to do a quick demo here with a somewhat simple component, which I think is a fun for the long time Linux and Unix users. So I'm gonna change my screen share real quick here. All right. Okay. So everyone should be able to see my screen. I'm going to zoom in a little bit. So what we've got here is, well, I'll zoom out a little bit actually, is Ferris says, and this is kind of like cow say, if you for those people who are old enough or Unix enough to remember cow say. We have just a regular component, and we can wash build it, right? So just a quick explanation. We've got the code on the left side, and we've got the a terminal open to the same folder on the right. So from the folder, we can do a simple wash build, right? And we get our component output, right? So we've got a signed component here, and we've got an unsigned component as well. If we're running in something else, like let's say a sort of less particular runtime, and what we can do is we always include with our examples, and this is an example that's in the wasmCloud repo, so you can look at it anytime. What we do is we always include a WADM file, a WADM file, depending on how you want to pronounce it. So this one is quite simple because Ferris says doesn't have any dependencies, right? It just takes in an invocation and it spits out text. So it's quite a simple application, but this is basically what it looks like. Very, very easy to grok. What we can do in this, is actually we could deploy this by just deploying the WADM file on the left, right? And that's easy and that's simple, mostly because we've done the work of writing the WADM file and making it simple to use. But what we want to do is to have this be a sort of no touch, no ups solution. And so what we've done is we've built wash dev to be able to to read your code, watch it change, build the component, spin up whatever WADM or whatever application manifest is necessary to run your application. And then what I'm going to do here is I'm going to call it. So I'm going to say, let's look at what's running. Let's look at my apps. So what I have is actually a wash app, a new wash app here. And this is from a previous run of the regular app. We have the dev version of the app. Now, note that all dev applications are ephemeral. So they're prefixed just to make it easy to sort of see which is which. And so we've got a new app here, which is dev prefixed, and it has a new little identifier, which you can see here, right? And we're going to get the inventory that is currently running on this host. So we're going to see all the different components that are running. And we're going to take this Ferris says instance and we're going to trigger it, right? Just to see what the output looks like. So this is now, and let's make an edit. Let's make a change. So we were wasmCloud users at this point, but now we're innovative, right? We've gotten our innovation day underway. So now we're innovating, I think. And that's it. That's all you need to do, right? You change the file. Our file watcher is very active. So you can see as soon as I made a change to the file, it already went about building. And you can just rerun whatever command you are running to actually test your application. And you'll be able to see the output and see the component and its requirements, its dependencies change in real time. We think this is really going to supercharge the development and sort of tighten the feedback loop for developing applications and trying to build with wasmCloud. So we're pretty excited about what this will do just to make developing applications for this new paradigm and developing applications in general much easier, much faster, and with less. To think of a good term for it, I think I'd call it just uncertainty around infrastructure, or sort of infrastructure nervousness that a lot of developers face, right? You won't have to worry about the infrastructure at all. You know, within, if we have interfaces that we recognize, we'll spin them up for you.
Hey, Victor, it's me. I had a quick, sorry, I'm not interrupting, right?
No.
Okay. I had a question. So because I had used WashDev before, and like at the time WashDev was very, start a component and then hot reload it, and that was great. But this iteration of WashDev is the hot reload, but it's not just that. It's also kind of like an infrastructure as code or infrastructure as component type approach here, right? Like this WashDev, the manifest that you're writing, that spun up more than just the component when you ran it, right?
Yeah. So this example is actually very simple. And the thing is, there are a lot of other solutions that try and do something like this, but what it ends up forcing the developer or the average user to do is to figure out how to deploy everything from scratch, sort of by themselves. And like for some apps, that's very simple. But the point of WashDev is indeed to start up your dependencies as well. Now, Ferris Says is a very simple app, right? It just spits out some text. But what we have here for apps that do, for example, HTTP handling, and this is why we included this particular example in the slides. If you require an HTTP server for your application to run, we spin up a sort of first approximation, right? We spin up a HTTP server, we hook it up to your component, and it's running, and you're ready to ping it. And so that's the very least we can do, and actually kind of close to the most we can do, because we can't tell exactly what your application does just by knowing that it handles HTTP requests, right? You could do absolutely anything once that HTTP request comes in, but we can at least make sure you have an HTTP request, make sure you have a key value server, make sure you have a blob store, things like that. And as long as you write to those interfaces, which is one of the core benefits of wasmCloud, you'll be able to run your app and test your app without setting up, additional infrastructure.
That's super cool. And this might give you a pretty nice segue. This should be able to work with the custom capabilities we've been adding to wasmCloud, right?
Yeah, absolutely. And that's, we'll roll right into the custom capability section there. Thanks, Brooks. What a great throw. wasmCloud is extendable, right? At runtime. It's one of the core benefits. You write your application, you write it to interfaces, right? To WIT interfaces that represent sort of foundational capabilities for your app, right? If you need to talk to a database, if you need to talk to a cache, if you need to handle web requests, or make outgoing web requests. And what we want to be able to do is that at runtime, we want to be able to switch out our dependencies, right? That's the point of interfaces, is that you don't have to care what the implementation is, the concrete implementation. So if you're doing key value, you might want to switch to, Vault, right? If you want an extra security, you might want to switch to Valkey. You might want to switch to Redis. You might want to switch to Couchbase. You might want to, for the really adventurous out there, you might want to switch to Postgres. It can do that. It shouldn't, but it can. And so we make sure that wasmCloud is extendable at runtime with capability providers. But more importantly, we have custom capability providers, which means if you have an interface, you can write your own interface, and you can make a provider that exposes that interface to your WebAssembly components and to other providers, right? So anything that can run on a wasmCloud lattice. So here, one of the most, I would say the most popular projects, most popular and influential open source projects is Postgres and is a database. It is a relational database management system. And we've spent a lot of time trying to make wasmCloud Postgres lean in and more specific to Postgres and its specific capabilities and its specific features, right? So a lot of the time when people build generic ORMs or generic interfaces to databases, you end up stripping away a lot of the benefits of Postgres or whatever underlying database is there. And just to get specific about some of those, things like the returning statement or being able to use data definition language like DDL inside just regular transactions is something that Postgres really shines at. And some other databases can do, but some can't. And we're able to encode that directly into the interface and not lose those benefits. And so that's really important. So you have both abstraction and you have really good concrete implementations if you want it, right? And if you need that that flexibility and that power. So we spent a lot of time trying to get this right, and so this meant basically going through Postgres and its offering, and of course not all of this list is here since it wouldn't in any way fit on a slide, but we've gone through essentially all of Postgres's types and mapped them to WIT. Right. So this means that you can deal with the full richness of Postgres types and Postgres functionality in WIT, but at the application level, you don't need all that complexity. You've got a pretty simple interface to deal with here. So here we've got at the top, 4 lines from the top here, we've got a query interface that all it does is take a query, which is a string, and of course, parameters, right? If you're listening to this, make sure you always parameterize your queries. Don't not do that. You know, it's been OWASP and security tip top 10 for what has to be decades now. But that is our default, right? So our default is for the query to take parameterized to take parameters as input. Those are safely decoded and used in the query, and then we turn what you can see in the towards the right here is a result of rows, right? And that's a simple interface, and that's the interface that your app will deal with. For those who need more efficiency, you can do prepared statements. Generally, most databases will support both of these interfaces and be somewhat separate, and give you an avenue for setting up a query to be run multiple times. Often, generic ORMs or generic abstraction layers don't have the benefit of being able to separate these interfaces and or add on specific database advantages that these interfaces bring. With wasmCloud Postgres, since we wrote this interface and implemented the custom capability provider behind it, we were able to make sure that we didn't lose that sort of robustness. We didn't lose the features in making our designs and our applications more robust and more easily spread and easily used in multiple situations. So here's an example of what it looks like to try and translate a lot of Postgres types to native WebAssembly types, right? So as people I think might not necessarily know, Postgres actually supports full text search, right? It's one of those things that sort of gets you going before you pick something that might be a little bit more fully featured. And it supports things like UUIDs. It supports things like containers, right? So the HStore is a bit of an old extension, but essentially you can think of it like a hash map, right? Like JSON before JSON was also supported, which is also supported by Postgres, by the way. So this means that you can express the full sort of range of Postgres types in your queries and in your code without doing a lot of driver-specific work in whatever language you choose, right? And again, this is leading into the benefits of WebAssembly and the benefits of wasmCloud, is that this is all relatively language agnostic, right? You don't have to worry about, oh, does my current language support, let's say like TS query or TS vector or like native Postgres UUIDs? Do I have to turn it into a string and then turn it back? Those things just sort of melt away. And over to the right, we have an example of what one of these queries would look like, right? For a very, very simple query, But there's a lot of, since Postgres gets a lot done with just the textual format, there's a lot more that you can do here. For those who are really adventurous, I'd like to point out that you can actually work with custom types here, right? So as long as you have, for example, a cast from your custom type to a type that's already supported, let's say text, you can actually completely use and make use of the native Postgres custom types and custom values functionality just without changing your interface here. Now you need to know much more about Postgres to do that sort of thing, because you need to define the casts and whatnot. But the full sort of flavor of Postgres, the full power of Postgres is available to you. And if you find something that's missing, we welcome PRs. Probably another database that I think most developers know is Couchbase. Couchbase is one of the leading document stores and general, just easy to use databases that developers often reach for. Like often reach for it first, they get in there, they get going, and they scale with it. And so we work with Couchbase to build, first of all, key value support. And just to make it really clear, we have WASI key value support here. This is subtle, but there's a point here, because what you can actually do is, let's say you don't want to actually take the time to go through and enumerate every Couchbase type or every Postgres type and build a completely custom interface. You can actually adhere to an interface that exists, right? So you can take just a slice of Couchbase that's great at key value and expose that via the WASI key value interface. And that's what we've done for the first level of Couchbase support. But we've also gone ahead and done the work to gather all of the features and all of the really good stuff that's built into Couchbase and have made a separate WIT interface that exposes that functionality more completely. So just to summarize again, you can go small first, right, and only just expose a little bit of the interface under a known standardized WebAssembly interface, or you can go and convert the whole sort of, let's say, type space, or just all the operations and functions that you can do with Couchbase. You can translate all of them with a completely custom provider. And here's an example of what we've done with regards to that completely custom provider. So we went through, we looked at what Couchbase has to offer, all the features, all the sort of robustness that's in there, and started to boil it down to certain interfaces. So on the right here, you can see that we have wasmCloud Couchbase, which is what we're calling that's the namespace and package for the WIT interface. And we have the document interface under that. So the document interface, as you'd imagine, deals with documents, and you can tell that's distinct from the key value, just a key value view of a Couchbase database. It's more document centric, and you can sort of bring off a slice of the functionality, focus and implement that really well, and just expose that bit. Of course, we expose all of it, but this is a short snippet of what it looks like when you write a provider that exports the Couchbase interface, and particularly to do with documents. If you were in a component and needing to use that functionality, so up top is a provider that's exporting the functionality, which is sort of making available the functionality. You can build a component which looks like the snippet on the bottom, which imports that functionality. So you can think of that as like makes use of the Couchbase document interface and exports an incoming handler. So just based on this WIT at the bottom here, what do we know? We know two things. We know that this component uses the document functionalities in Couchbase, and it responds to HTTP requests. Now, what this component actually does, we can't tell from just from the WIT interface, because semantics, and there's the rest of draw and the rest of the OWL here. There's all of computer science is sort of up for grabs there. But we do know two things. And sort of cutting back to things like washdev, if we know that you import the Couchbase document interface, we know that you need a Couchbase server, right? We need that you need something that looks like Couchbase running So we can kind of, spin up that dependency. And if we know that you export the WASI HTTP incoming handler interface, we know that you handle HTTP requests. So what do you need? You probably need an HTTP server. So this is where a lot of, it's sort of the meeting point of a lot of different platform and ecosystem and technology benefits that all come together to give us more visibility and more functionality in our apps, and to be able to do more from just the description. So if you dive in to the document interface, what do you see? Like, what does that look like? So you get, basic types, right? Document IDs are a type. Durability level, which is something you should really look at if you use Couchbase in production, and you should know about. And just basic functionality like CRUD, right? Being able to insert a new document with a new ID. And all this functionality was sort of pulled and distilled from the Couchbase Golang SDK. And it maps almost one-to-one. Of course, we'd love to hear if you find any points that don't match up or don't feel ergonomic. But we've taken the decisions and the sort of time-tested traditions of the Couchbase team in building their SDKs, and in particular the Golang SDK, and sort of bake that into our interface. And what we want is for this interface to be used across languages, right? So taking the decisions and the good bits of the interface and making sure all languages can access this, and it can be accessed across a variety of ecosystems. So this is all really exciting for us, but it's more exciting when we build things together. We want people to get excited about defining interfaces and building the providers and even components that satisfy those interfaces. Couchbase is an example of this, and we're very excited about it. And Postgres is an example of this. And we have HTTP server, we've got KV, we've got secrets, we've got so many examples, but we're ready to get blown away by what other people are excited about and what providers they want to build. So we've got a repo called wasmCloud contrib. So under the wasmCloud org in GitHub, we've got this repo, and we're excited, and we want to see even ideas of what you want to build. If you've got an idea for a new provider that you think would be cool, make an issue or just write some code, throw it up, and we'll take a look, and we'll consider including it. And we're pretty excited, and we want to see what you can build and what technology you want to expose. Just cross ecosystem in this new compute paradigm. Oh, and I spoiled it a little bit here, but what's coming up.
Hey, it's not that bad. Get people excited. Victor, I know that, well, we are running a little bit short on time, but I just wanted to ask really quick. So all the things that you built and collaborated with Couchbase on for the Couchbase WIT and the Postgres provider, or the Postgres interface, all of that is a WIT interface, so it can be used in any language that supports WIT and all that fun stuff. But it was all a part of our custom capability support, right? Like there wasn't anything that was there anything that you actually needed to change in wasmCloud to support Postgres or Couchbase here?
No. Yeah, that's a great question. So the point of it being custom is that, yeah, you can, with the same platform underneath, you can build providers and build new functionality without changing the rest of the stack, right? So we took a look at Couchbase. We looked at the interface the sort of natural interface that they form with their SDK and with how people are expected to use Couchbase, and we just boiled that down to WIT. And we slotted it in to the existing ecosystem, the wasmCloud ecosystem. And then we built a provider that exposed those interfaces, all without changing all our apps, right? Building new apps to use that new interface is one thing, but not changing existing apps, not changing the existing host, and not changing anything we'd set up already. So it was really smooth from that point of view.
Awesome. Awesome, awesome. I know that was a huge goal as we went to 1.0 was to have that extensibility. Great.
And the fun part was really just digging into Couchbase, and obviously Couchbase worked alongside us, and it was really awesome to sort of crawl along all the sort of corners of what Couchbase can do. And I learned a lot just about things Couchbase sort of has in its back pocket and a lot of the awesome features.
Awesome. Well, thank you so much, Victor. Yeah, as mentioned, we're just going to keep rolling on through here. So again, if any folks have questions, please keep throwing them in the Q&A. This has been really awesome to engage there. And what we can do now is give it back over to Bailey, our fearless keynote leader, to talk about machine learning. So Bailey, go for it.
Great, thank you. Yeah, as you probably are aware, AI and ML is a very hot topic right now. And I wanted to be able to break down and give a sort of a simplified overview of all the different approaches that I've been seeing. I'm going to focus here specifically on inferencing style workloads. And one of the things that I find most interesting about this is that WASM is an excellent compilation target for these types of workloads. And there are basically four main categories that I'm going to walk through: WASI-NN, WASI Web GPU, compiling models to WASM, and then also writing your own custom interfaces and providers. And I want to note that all of these different approaches are also compatible with wasmCloud, but I'm actually going to give many different examples that I'm seeing around the industry today. So for WASI-NN, it is a WASI interface for performing ML inferencing. It's been around for a couple of years, actually. One of the key champions, Andrew Brown from Intel, has been pushing it forward and evolving the spec for it over quite some time. We've had some very recent and very cool additions to that spec to make it a little bit better for the types of inferencing that I'm going to demo in a second. It has many different key pros. It integrates actually with your existing models and ecosystems that we have today. That space has exploded. So trying to create something that allows you to sort of abstract all of those is really incredible. That's one of the biggest strengths of it. Of course, it's a WASI API, which means that we're seeing many different runtimes implemented, from WAMR to WASMTime and WASM Edge. And by far, the biggest strength for WASI-NN is that it allows for hardware optimization, and that essentially you tell the API to load your model and then run inference on it. And that inferencing side actually happens with host code, with native code. That's both its greatest strength and its greatest weakness. The reason why it's a bit of a weakness is that it makes it very difficult to sandbox, and also because it ties itself to hardware, it makes it not portable. However, if you are deploying your own inferencing models, it's your first-party code, then perhaps sandboxing is not as big of a deal to you. And if you already have an ecosystem that has this large investment in existing models and complex use cases, WASI-NN is a great solution for you. The other one that's emerging, but really, if we're being frank, it's very nascent, but I get asked about it a lot, so I wanted to give a bit of an overview of it. This is another new WASI interface called WASI Web GPU. And given the name, you can probably guess that it's based off of the Web GPU API, and obviously targets GPUs directly. Because it targets GPUs directly, that means that you're probably not going to have some type of CPU fallback or be able to take advantage of specialized hardware like TPUs that make it very efficient for running TensorFlow. However, its biggest pro is that it's extremely portable. A lot of places have already figured out how to support a web GPU API. It also is a lower level fundamental building block, and I find that extremely exciting because what I expect to happen is that many different people are going to build AI frameworks on top of WASI Web GPU. However, that hasn't quite happened yet, so there really aren't many off-the-shelf solutions for it today. Now, if you're a pioneer or a bleeding edge seeker, this is probably the time to jump on this bandwagon and see if you can build out your own AI framework for other people to use. Now, this is another case that I think is actually probably something that you've run and you just didn't realize. That's because TensorFlow.js seems to appear just about everywhere in major web applications. It's very handy for, let's say, blurring your video background. Now, there's another case that I think is interesting that I'm seeing a little bit more on the server side, which is compiling Llama 2 specifically, so a quantized version of that model, to WebAssembly. And when you compile the model and all that it contains into a single .wasm, that's really nice because that means any WebAssembly runtime is able to run it. And that allows you to do local first style workloads. You don't have to make a network request to run your inference. You don't have to step out to a separate process. It is literally all local. And that means that it's all sandboxed inside the WebAssembly runtime. Now, there are some significant trade-offs for this. The performance is probably the biggest. Inside WebAssembly, we've been pushing forward SIMD 128, so an expanded SIMD. So there is new performance gains, but at the end of the day, you're not able to take advantage of specialized hardware that loses the portability of WebAssembly by using this approach. And it also expands the code size footprint quite a bit. So if you are interested in this type of approach, which many people do because they're targeting the web or edge or local first use cases, do make sure that you use a quantized version of your model, aka something that's more compressed and smaller. All right, this last bucket here, I'll admit, is very much a catch-all, where we're seeing people write custom interfaces and providers, and the degrees of what this implementation looks like varies wildly. But I want to just give a shout out for a few different approaches. Wasm Edge has a number of different styles of how they can support AI inferencing. One of those is with a TensorFlow interface. So in a lot of ways, that's like a lower level API that's very specific to TensorFlow. But if you are running with only TensorFlow, then maybe that's the best API for you. There are also lots of other cases that I'm seeing where WebAssembly components surface an OpenAI HTTP interface that other people are able to call into. But what happens underneath is still a little bit of a varied story. How they actually are doing the inferencing seems to be very widely different between different providers. And this last one is one that I want to dive in a little bit deeper. Some folks are building APIs that are specific to certain providers. For example, Ollama. So earlier today, I showed the wasmCloud space demo, and that actually uses Ollama under the hood. Some key pros for Ollama. We've got so many different models there. A lot of these are open source models that you can pull down and run on your laptop. So the demo I ran was on my laptop with running Ollama with their desktop app. So it has a ton of different desktop apps for Mac OS, Windows, and Linux. So it's really great for consumer hardware. And it knows how to fall back to a CPU if it needs to. That makes it perfect for local model deployment and development, and makes it very, very easy to use. Now, there is a big con, although to be fair, this is a problem that we're trying to solve across the industry, and that's you can only run one inferencing at a time because it's kind of hard to figure out a way to multi-tenant your GPU. So if you're using Ollama, I really recommend it for local and edge applications. Understand that you're going to have some type of workload lock before executing on your GPU. So make sure that you think about that, and also understand that this is really a privileged capability. You're giving access to running inferencing on a GPU. And with wasmCloud, you're able to give that capability through a link. And I'll show a little bit of what that looks like inside the demo. Now, we're going back to the application architecture here, and I'm going to talk through this component specifically, the image analyzer component. It's the one that triggers our inferencing on, runs image classification against the image that we upload. There's another piece here that also uses a blob store bucket. But let's first run through and remind ourselves how this demo works. Again, I've got a globe. I'm going to use some different images this time. And the job of this image classifier is to determine whether or not this image is a ship. So I have a Corvette running on top of water, so it's kind of confusing. Let's see what the AI does here. Okay, this Corvette is not a boat. Let me give it a real boat. So this is an image of a boat. Let's see whether or not it determines that that image itself is a boat. Okay, it is a boat. Let's look at the code on what is making all of this happen. My component here is the image analyzer.wasm. It's 292 kilobytes, so extremely small. Compare that to a container that's in orders of hundreds of megabytes, even gigabytes. And what it's doing here, we're going to step through the logic a little bit since it's fairly straightforward. We essentially have it making an OpenAI HTTP call over to Ollama that's running locally. Ollama surfaces and supports OpenAI compatibility over HTTP. So if I'm configured to talk to an endpoint, I'm going to call that endpoint here. And then I'll also be able to pass in a prompt so that I can, configure this actually at runtime. So one little piece here, this code is WASI config runtime. So it's my ability to change and modify the config at runtime. And how do I do that? I do it by working within our application manifest. This is my component getting pulled from OCI, and here's my runtime config. And notice that I have a very simple prompt passed in here, but I can refine it and make it better at runtime as I want. And it's linked over HTTP, so that's the part that's making the request over to Ollama. And then it's also managing the tasks that I'm working with within this component. One other thing I want to highlight is that I did mention that the image processor, so once we've processed an image, we said, oh, it's a boat. Let's save it and process it later for more things. Let's upload it to a blob store. So I link it to a WASI blob store. But what's really cool about this is that I can actually use and swap in a capability, in this case, a blob store that's my local file system. That is really, really powerful because it means that I can take the exact same .wasm that I'm developing locally, working with Ollama deployed on my desktop, and then when I deploy it to production, it's still making OpenAI API calls. So I could back it by OpenAI provided by Microsoft. So, and also a blob store, let's say, with Azure. It's very, very powerful. One last thing I want to show here is that when I look at my component to see what it has inside it, I run this command called wasm tools component wit on top of my image analyzer component. I'm outputting it to component.wit, and you can see the things that it needs to be able to run. There's that WASI config runtime import, and then all of the other different WASI pieces that I use to be able to execute this component. So that is a very brief overview of how you can write your own component using Ollama and our Ollama provider. So let's keep rolling because I know that we're a little bit tight on time. I am happy to take questions, but I, am also really interested in listening to Taylor and Roman dig into wRPC and NATs.
Yeah, Bailey, I want to ask you a bunch of things, and I agree. It probably would be best to just kind of keep on rolling through that session if that's okay.
Totally cool with me. I'll be online.
All right, then Roman and Taylor, take it away.
And just a note, you will be able to talk to all of us in this collaboration session later. So now that you've seen all this magic, one of the last things we wanted to show you is kind of how the magic works underneath the hood, to show how this is all happening and the approach we took and why. And so Roman and I are going to chat a little bit about this technology called wRPC and NATs, which is what we're doing underneath the hood. So let's go ahead and talk about this. So we have this need for a component native protocol. That's basically where all of this started from. So WebAssembly's main superpower is this whole interface-driven development thing. There's been questions in the chat about this where it's like, well, how do I change out a provider, end of life a provider, or change? That's the nice thing about this is it doesn't matter as long as it implements the same interfaces. And this main IDL that we're using, this WIT, is very powerful and includes a lot of features that aren't found in things like OpenAPI or like gRPC, those kind of tooling of modeling out an API of some kind, because you're modeling out directly like you would a library that you'd expose to anybody else. There's things like passing by value and passing by reference, streaming things. There's all the security benefits of WASM, but also the component model has this nice nifty feature, which is a kind of a key thing to make it work on any platform and any architecture, is that it does what we call the lifting and lowering, the translation of the types as they're represented in one language to the types as they could be represented in another language. And so with that, you're able to basically get cross-language things and all the translation between those for free, because you have WebAssembly being this format that is supported by all of these different languages and platforms. So this is where wRPC came in. Now, wRPC is a project that has been upstream to the Bytecode Alliance. It originated with us in the wasmCloud project, but obviously we wanted this to be something that's bigger than just what we have. And that line we have on the slide right there, the component native transport agnostic RPC protocol, is the key thing here. So wRPC is broken up into transports and as well as like the main protocol itself. And so what we do is we take these things and we're able to encode these values and send them everywhere. So wRPC actually supports QUIC. It supports NATS as a transport, and soon it'll be supporting TCP as a transport as well. But basically anything can be used as a transport. Now, something that's really critical to understand here is this is not a wasmCloud specific thing. Because this encoding is the exact same, the way you encode these types is actually part of the WebAssembly specification of the component model. And so this uses that same encoding. We're not defining a new encoding type out of whole cloth. We're not just coming up with our own thing. And this is really important because this is what we figure will be the basis for extending hosts. Because what a lot of people do right now in the Wasm space, and this isn't what wasmCloud does, we use the providers, is they bundle in dependencies into their host. So if you wanted to do something like the Redis or the Couchbase thing, you'd have to compile the Couchbase client into your host to get this functionality. And obviously, like for a short-term thing, or if you're doing something very specific, that's fine. But for longer term, that's going to be a security nightmare. You're now bundling all the dependencies into your host. So this is the basis for something like a host plugin model, where you can say, oh, here's and that's what a provider is. It's basically a host level plugin that allows you to expose these capabilities, these interfaces to everything else running. Now, like we've kind of mentioned before here, wasmCloud is using NATS as our wRPC transport here, and that's where a lot of the magic happens. So there's a couple ways to note how this all works. Now, wRPC gives us essentially 4 ways. Well, the component model plus wRPC gives us 4 ways we're able to satisfy imports and exports. The first thing is imports can always be satisfied locally or basically embedded in the host. Think things like clocks or randomness or those kind of things. These things can always be pretty much in any host. They don't have to be. You could technically distribute them, but they are often local capabilities. The other thing that can happen is you can compose the components. Bailey showed this in her slide several times as well, is you can take 2 different components and they can satisfy an interface, and that interface no longer appears publicly. Then you start to get into the wRPC level. So wRPC can let you do a process that's external to the wasmCloud host. And this is what happens on like a provider on a single host. It's still running on the same machine, but it's external to the actual wasmCloud process. Then the last is that it also enables you to do it distributed over an entire network. So your capability could be running on an entirely different host in an entirely different region with an entirely different architecture, yet it's still using the same WIT interface that it expects to use. Nothing here requires something special. You can use the same component with that interface locally that you would in a distributed environment. So this means it's completely WIT native and it's extendable at runtime, and it still has those security things that come in from the fact that the transports have TLS and all that, plus it's still obeying all the rules of the component model. And I'll go ahead and pass this off to Roman because I've talked quite a bit. And Roman's going to show you how this actually works with a real live demo and seeing it actually in action here. So I'll let him go ahead and take the reins.
Thanks. Yeah, so I'm going to walk you through a demo of which is actually available in wRPC repository, and I'm going to serve WASI key value, and I'll do that in actually 3 different ways. So I'll have a native Go application serving WASI key value. It's a regular WASI key value with using wRPC over NATS. I'll also have a Rust native application doing the same thing. And then I'll have a Rust component also serving WASI key value. They're all going to just have a simple in-memory hash map implementation. And the only way how on the transport layer I'll be able to differentiate between them is by using their NAS prefix. So it will appear as a prefix in the topic on which our NAS subscription is going to be set up. I'll then have also 3 different clients, again, using regular WASI key value over wRPC using NAS. And so again, I'm going to have a native Go application, native Rust application, and a Rust component. I'll then use a single, my client to call each of these servers. And finally, I'll also use each client to call each server. So let's see how this all works. So I'll start with just running my Nets server in trace mode so I can actually see every single subscription on my Nets cluster. So let's take a look at the server components we're going to use. And as I said, it's a very simple component, which is just going to just really wrap a hash map, right? So like a get, for example, is just get a string, look up that key in the hash map and get the bytes out of it. That's it, right? So it's really, really simple wrapper. And there's nothing specific to wRPC here, right? It's important to know that this is really just a regular WebAssembly component. There's nothing, like it's not aware of wRPC in any way. So to make this work, I'll actually use a runtime, which is going to be wRPC wasm type nats. That's a tool provided by wRPC repository. And so it's really just a wasm type embedding, which has a wRPC integration and which uses nats as a transport. And other than being just a regular wasm type embedding, it will just do two things, right? One of them is going to be it's going to always inspect your component because your component is actually a self-describing service. It's sort of like a self-describing microservice. And so for each import, which is not already satisfied by regular wasm time, everything from custom import, some function that is your application specific, it will satisfy all these imports using wRPC over nets. Similarly, if your component exports something, it will be re-exported again on nets using wRPC. And so to show that in action, I'm going to build my component. I'll target button 32 as a preview one, just because it's currently stable in Rust. And then I'm going to service. I'll specify a prefix of wasm, meaning that all my functionality is going to be available at the prefix of wasm. And you can see right here in my nets log that this is the key value store interface. And so by running this component, my runtime actually inspected the component, and for each function which was exported by the component, it set up a subscriber on nets. I'm going to move this right here. And so let's take a look at, for example, doing this using the native code, right? So let's see, it's Nets server. And it's going to look very, very similar. Like for example, let's take a look at our get implementation. So here it is. Again, it's going to be just a similar, hash map and just doing just the same thing. The only difference is that now we use with Bungee wRPC rather than upstream with Bungee for components, because here we're targeting native applications. And then we also have a main function because that's a real, route application that can just cargo run. And I'm just going to do just that. I'm going to run cargo run my key value nets server, and I give it a prefix of Rust. Again, in our nets log, we see that there's 6 more subscriptions. And again, it all looks exactly the same except for the prefix, this very first, element there in that topic. So now I can do the same thing for my Go server. Again, it's just a regular Go application. For this particular one, I'm going to have to use Bungee, again, provided by wRPC. It's very similar to, again, upstream with Bungee, except it generates with bindings for wRPC for native applications. And again, it's just going to wrap, in this case, sync map, which is the Go alternative, so, hash map, which is safe for current use. I'm going to run this with prefix of Go. So at this point, I have 3 different servers running, and you can see here that I serve my WASI key value 3 different ways. And so finally, I can actually invoke these things. So let's take a look at our client. It's going to be a very simple application. Again, just a regular WebAssembly component. It's going to open my bucket. It's going to set some key foo to bar. Now it's going to check if it still exists and check the value of that. And then finally, list all the keys in my bucket and just print them as timeout. Again, I'm going to build this. This case, build the client. And now I'm going to run it using the runtime, which we've seen before. As you can see, right now I invoked a prefix of wasm, right? And so my invocation was handled by that component running in my runtime. right? So similarly, I can target, for example, my Go application, and here we see in the log that my Go server just handled this this invocation. And similarly, I can target my native Rust implementation. So just the same way, of course, I can invoke all these things using my native application, native wRPC services, let's say, or well, consumers. And so, for example, here, I'll use my Rust native application, and I'll just give it a prefix. I'll just call all three of them simultaneously, and perhaps I will have to see. I'll do it again. Here we go. So each tree of my servers just got that invocation. They serve that, and that's why you see the logs happening here. And of course, I can do exactly the same thing with my Go native application, again, using WASI key value over wRPC over nets. So with this, we've just seen this whole, this is what we just seen, right? So we had a native Go application calling, each of these servers. We had native Rust and also a component. And all of these were speaking WASI key value using wRPC over nets. And like for my runtime, for example, I didn't have to do anything special. Like my runtime did not have bindings for WASI key value. Instead, all of this functionality was just inferred directly from the component itself, from its interface type. So with that, back to Taylor.
Awesome demo, Roman. So this is I love this demo because it shows like how flexible this all is. To reemphasize again, everything here is standards-based. So the whole purpose wRPC exists is to provide a standards-based approach to distributed communication for these components that we leverage. And what this lets us do is what I'm showing now in this kind of diagram right here. You're able to get that wasmCloud space demo where we're showing, hey, there's all these different things we're running across different locations, and we could be running across something that's on the edge or something that's really close by. You're going to see some of this actually from some of the users in the community who will be talking today. But essentially, you're able to leverage the powers of NATS, which in this case lets you do what they call a geo-aware supercluster, where something's distributed. There could be me in Salt Lake running in a little Leaf node that's out like here in my house. And then you could have something running in US West and US East and EU West. And all of these things can then distribute it. So in the key value example Rowan was showing, the Go thing serving up a key value could be running like in EU West. And if something comes into US East for an HTTP request that's then going to use that key value, it could go to EU West, it could go to a local one, and it's able to do that basically automatic failover, shortest path type stuff that NATS lets you do. So it lets you be completely scalable, and it does have that reliability aspect I mentioned, but it's also geo-aware. You're able to, because it's using those latency graphs, it knows exactly where to go to make sure it's reaching its closest target. So you're able to build some really, really interesting applications this way. And that's kind of the underlying magic here of what's making this all work. So with that, I'll go ahead and hand it off to Brooks.
Yeah. Wow. Thank you, Taylor. Thank you, Roman. Again, just like Bailey, I have many questions and things that I'd love for people to hear more about. We are running up pretty close on our schedule, though, so I think we're just going to keep rolling through. I'm going to go straight to the wasmCloud community meeting. But folks, I do see there is a question in Q&A, so please feel free to ask Roman and Taylor questions, because this is it's got to be the coolest thing that we do with wasmCloud today. All right. Well, I know that, let's see, I've got about 8 minutes to go through this one to keep us on schedule, so I'll do my best. So welcome, everybody. This might be your first wasmCloud community meeting, and so I want to take you through a little bit of an orientation. Every Wednesday is wasmCloud Wednesday. We have been doing a community meeting at 1 p.m. Eastern Time on Wednesdays, every single Wednesday for the past 3 or 4 years. Never missed a Wednesday. It's pretty wild. And you can see all kinds of information about that at wasmcloud.com/community. Everybody is welcome to join in a Zoom, kind of exactly like this one. Come in, ask questions, do demos, contribute to the discussion. And we also live stream it to YouTube, kind of the same as we're doing for this Innovation Day. So to make sure that you are continuing to stay involved and can attend our future community meetings, make sure to join our Slack. It's wasm, or slack.wasmcloud.com. There's a link at the bottom of our website for all of these as well. You can watch past community calls from the live streams. And you can also actually add a wasmCloud calendar to your Google Calendar, which contains, I believe, a few WASI WebAssembly standards body meetings. And it includes this community meeting to make sure that you don't forget, and you can always find the Zoom. So let's go ahead and keep rolling here. I want to go through the agenda for this community meeting. This will be nice and short and sweet. So if we go over to the wasmCloud site, we can go check out the agenda for today. So I am going to do a quick tour through the wasmCloud component crate, and then we'll talk about contributing and being a member of the wasmCloud community and suggesting features to our roadmap, which is really fun. I'm going to do a quick shameless plug if you haven't yet. I see a lot of you on stream. Go ahead and throw us a star on GitHub. That really lets us know you're watching, and you'd be super cool for it. All right, let's go ahead and move on to the wasmCloud component crate. So you earlier saw some examples from Lucas on the component SDK for Go, and we've actually been working on a pretty lightweight version of this for Rust as well. And this is newly published on crates.io. Okay, sorry, I thought okay, audio is coming through fine. Newly published on crates.io. We've been using it for our test components and examples for quite a while, but you can actually import this into a component project now as well. And to give you a brief tour of what's available now, we have top-level macros to proxy to WASI logging for the standard logging levels like debug, error info, which is really nice to be able to just use these macros like you do in idiomatic Rust. We have additional structs and implementations for standard library crates, and a couple of helper functions like for working with WASI.io pollables. You can poll a list and wait for them all to complete, which is really useful for functionality like making many outgoing HTTP requests and then polling all of them until they're complete, and then being able to handle those all at the same time. So we have two modules in here. And these correspond exactly to how WIT-bindgen generates types. So the goal is that you can bring in the wasmCloud component crate and use that directly in a component application, the same way that you've been using WIT-bindgen. And it provides just for a little bit nicer of an experience for working inside of Rust. And all this is really doing is doing the WIT-bindgen interface generation at the crate level, which this is something that is a pattern that's going to be very prevalent with any WebAssembly crates in Rust. You can see, for example, wasmCloud messaging consumer. This is how it gets generated from the WIT. You have publish and request. If we go back up to the top level, we can see under WASI all of the, or at least many of the interfaces, no, it's all of them, that we support with wasmCloud when you run from WASI. So if we take a look under key value, for example, you can see atomics and store, and under atomics, the function like increment, for example. These are all of what you generate locally. But what this means practically, I have this example component, which is the HTTP key value counter. And you can see that the changes that I made in this little example. I have kind of the diff pulled up, where instead of using WIT-bindgen to generate all of my types and using WIT-bindgen as a crate, I'm actually just using the wasmCloud component crate in order to import the trait to implement for WASI HTTP incoming handler, the types for WASI key value and wasmCloud bus lattice. And then I've gone ahead and swapped some of those out, the generated code, for using the crate directly. So the wasmCloud component crate here essentially is this one-stop shop for all of the interfaces that we support natively with the wasmCloud runtime. Now, this is really nice for when you're working with all the standard capabilities. This is also completely compatible with using WIT-bindgen in addition to using the wasmCloud component crate. So there's nothing wrong with continuing to have a WIT folder, continuing to use your own custom interfaces. That will integrate really well into this too. Now, one additional benefit that I wanted to show off here in doing this is it's not just that you get you get to kind of skip the bindgen step. We also have additional trait implementations in Rust, which really provides a nice experience. So if I bring in the standard IO write trait here, I need 2 colons, then instead of using the generated type blocking write and flush, with the wasmIO output stream, I can actually use the standard IO write function that is called, I actually want to use write format. And then, thank you, GitHub Copilot, you're doing a great job. I can use this format args macro from the Rust standard library and just directly write this formatted string as bytes to the output stream. I saved it down here just in case GitHub Copilot didn't save me. So in doing so, now I'm not using the generated type. I'm actually using a standard library function from standard IO write to operate on this wasmIO output stream. And this has got to be one of the most useful ways to interact with the with streams is just by using standard Rust library functions. And that's super nice. Last but not least, just to show you here at the end, even when you use the wasmCloud component crate to do this, you are compiling a component directly down to the standard WASI interfaces. So the only thing you'll see in here, which is the wasmCloud custom interface for bus, everything else is using WASI CLI, WASI key value, WASI HTTP, all that fun stuff. So wasmCloud component is out now as a crate. We're going to be doing a couple of iterations on making sure that our examples are all up to date and using this crate. And also a huge shout out to the WASI crate, which provides a lot of these common bindings that we have kind of namespace under wasmCloud component, WASI. So I think the TLDR here is you can look forward to a more crate native experience for wasmCloud components, and you can use this right out of the box with just running in Wasm time as well. I'm going to run over maybe 2 or 3 minutes on time, but I think it's important. So that is all for the demo. Normally we pause for questions and everything, but this is a good preview for your first community meeting. Next on the agenda, I wanted to just go through 2 quick discussion items. We are coming up, well, I'll talk about that in a second. The first thing is if you're wondering, this is an awesome ecosystem. All these people who are presented today are so cool and I want to be involved with them. How do I become a contributor? I would first and foremost recommend coming to the wasmCloud repository on GitHub. This is the main repository where we do all of our development. And if you append /contribute on the end of the URL, that will give you a quick link to our contributing guidelines and then highlight all of our issues that are marked as a good first issue, which also we try as best we can to tag these as the language that you would be writing to help contribute and the project that it pertains to. So you can contribute to our CLI, our core runtime, our application deployment manager. There are many, many different ways to get involved. We even have a wasmCloud dashboard, which is using React. So if you're a JavaScript or TypeScript developer, you've got a perfect place to jump in. Last but not least, on top of for contributing, if you have an example component or capability provider, we have a wasmCloud contrib repo, which is a catch-all for all things community contributed. And essentially, if you've implemented it and it uses wasmCloud in some form or another, we'll take it. And we want to really create a safe space for people to contribute what they've built in wasmCloud that doesn't feel as high burden of contributing to the main mono repo or trying to fit it in with an existing repo structure. So please take a look here if you've got something you'd like to contribute. Okay. The last thing that I wanted to cover today in the community agenda is just to really emphasize that wasmCloud is a community-led project. The last 2 quarters, we've been doing quarterly road mapping planning in the wasmCloud community meeting. So about 2 weeks from now, we will do our quarter 4 road mapping session. And all of the sessions or all of the issues and improvements and new features that are on the wasmCloud roadmap, we came up with during that session. So you can see that tracking in GitHub projects. We have a whole write-up, and you can see tons of community members taking the items from this roadmap, which just makes me so excited. And really the call out here is we would love to hear your feedback on what features would be most impactful as you start using wasmCloud. And all of that contributes and becomes the next roadmap of what we're working on as a community. So please contribute. Thank you so much for coming to your very first wasmCloud Community Day. wasmCloud Wednesday. Really looking forward to the future attendance for you all coming to the future community meetings. And yeah, I think I'll leave it at that. So I want to wish everyone to have a wasmCloud day as we get back to Innovation Day. And I believe now is a good time to transition over to Bailey Hayes and Joshua and Luke, who are going to be participating in the Fireside chat with some of the prominent members of the Bytecode Alliance. So I'm going to stop talking now. Bailey, take it.
Thank you, Brooks. Really appreciate it. You're always just such an amazing community leader. And with that, I want to introduce two other amazing community leaders. Now, they are leaders within the WebAssembly space, WASI, and inside the Bytecode Alliance. That's Yash from Microsoft and Luke from Fastly. There's so many things that I could say about you guys, but since we are 5 minutes behind schedule, I think we just jump right in. What do you think? Okay.
Sounds good.
Let's start with what are the types of things that we are working on right now. Yash, I know that you've been doing a lot of work in the WASI space on us being able to iterate. Do you mind speaking a little bit about that type of work and what we're trying to do there?
Yeah, absolutely. So WASI, as we know it, first, I don't want to go like a full history lesson, but like, WebAssembly came before WASI. WASI was released as a snapshot, sort of like hey, we want to like get a thing out there back in 2019. And then a pretty long time passed where a lot of very like good development like happened. And we were like, oh my God, like we need to like do things better. Sorry, I'm stumbling over my words here where I'm like, what do I say? Anyway, 2024, we released WASI 02, and everyone was kind of like, okay, great. We have a good foundation now. And what we'd like to do is, by the way, if you can see a cat behind me, that cat is causing trouble. But yes,
Hi, cat.
in 2024, we released WASI 02. And from there, we were like, okay, we don't want to like wait another like X number of years. Instead, what we'd like to do is get into a iterative development process. So I want to say August, we released WASI 021. Now in 2 weeks, we're going to be releasing WASI 022. And 2 months after that, we're going to be releasing 023 and so on. In order to do that, we had to like figure out new language features, figure out the process, and that's been like really fun and involved. But we're having steady releases now, and that I think that's pretty exciting.
And I know I want to give a shout out to all the different contributors that were involved for that. I know Alex did a ton of work for semantic versioning, both in WASM time and in WASM tools. So both on the guest producer chill chain and on the host side. Luke, this is largely your design. How exactly are we able to evolve WASI when we got so stuck for a few years? No judgment. There were a few things that happened then, like COVID and job changes and all of that kind of stuff. But how exactly, like, what are the mechanics that let us be able to do this?
Yeah, well, I guess what was really hard was we had this goal, which we all agreed ahead of time, which was like we want WASI to be modular, broken into different chunks of functionality so that every host doesn't have to implement everything. You don't have to both be a web server and have a GPU and have, access to a mouse all the same time. Like you get to choose which interfaces make sense for you to provide. So we're like, yeah, abstractly, that totally makes sense. It was in like the original WASI blog post, but we're like, actually, what are the mechanics of defining modular interfaces that kind of relate to each other and kind of share types sometimes? And also, how do we do it in a way which allows us to have components, which are like small isolated building blocks where every component doesn't have access to all the functionality at the same time? So we needed a thing to base kind of like a foundation on which to define WASI, and that's the component model, and then a language to write our interfaces in so that that was language agnostic and allowed us to generate the bindings that we want, and that's WIT. So I think those core building blocks that came in with Preview 2 was what's the component model and what's the IDL we can write in, which is WIT. And so now we have them, they've stabilized, and so now we can, with that stable foundation, start talking about what's a version of a WASI interface and how do we, in a mature, regular way, increment those versions.
As you said, we in August released WASI 021, and we're aiming towards 022, October something, 10th or 1st, something like that. In October, that's probably good enough. The first week.
Yeah.
What was in WASI 021? What was its purpose?
I'm looking at Luke here, and I feel like the answer is like less than what we hoped. But I think we got like a fair bit in. Zero. Yeah. So 021, I think you can best think of it as what we really shipped was we shipped a release process itself. So, you know, it's often like very easy to look at a change log and be like, hey, what are the code changes? Or what are the features? And like forget about like the process that goes into making these things. So in order to ship 021, we had to define a process, which was multiple months of like, you know, figuring stuff out. We had to implement the things. Once implemented, we had to like make sure that they actually worked. So there was like a fair amount of like infrastructure changes happening in Wasm time, in Jaco, in all of these things, making sure the design is vetted, making sure that the spec is up to date. Things like language features for WIT specifically. We added a gate notation, which is not a generalized feature gate notation, but or like, you know, attribute system, but like just for this at since and at unstable. Can you hear the cat crying in the background? Because she's howling at me. How dare I be on a meeting? But
It's
yeah,
cute.
like sorry, it's very distracting. But yeah, we got all of that out of the way. We got all of that implemented, vetted, making sure that that was right. And then 021 rolled around. And what we essentially did is we bumped a bunch of versions and we validated that, hey, we can in fact bump versions and nothing falls over. And that was a pretty big deal. Yeah.
Yeah. Can you describe what a release train is? I think some people might have seen that's what WASI effectively adopted. What is it?
Yeah. So a lot of us like come from Mozilla and other projects, but yeah, I'm former Mozilla by way of different companies. Luke is also former Mozilla. You know, like at Mozilla, the Firefox browser releases every 6 weeks. That was adopted by the Rust compiler as well, which also began releasing every 6 weeks. They're like different nightly versions that release more often, but the major versions release every 6 weeks. Wasm time itself has a similar release cadence. And for WASI, the specifications, we knew we didn't just want to like do the big like waits between versions or like have a irregular release cadence. So it was like, okay, do we wait for specific versions or do we do it on a timeline where timeline sounds good? And rather than 6 weeks, which is a little tricky to manage because it, you know, our calendar is like base 12 for months, not base whatever, you know, what, 6 times 12, some 72, or I don't know. It doesn't do that. So we're like, let's do every 2 months. Let's make sure every 2 months we bump the versions. We make sure that whatever proposals have been accepted and voted to progress to stable, which for us is like we call it like stage 3, phase 3. I forget the exact word.
Phase 3.
Phase 3. Okay, yeah, that one. Once they're in, then we say like, okay, this is going to become part of the next WASI release, and then we release that out and we say, here's a nicely packaged thing that we give it a version, and then we can talk about it. We can tell people like, hey, these APIs are new, or here's what you can do with it, or maybe we include deprecations too. But that allows us to like better talk about it. Yeah, it happens every 2 months.
Yeah, so after establishing this process, effectively what we're saying is that we've got these processes in place, we've got the mechanics rolling, and we're able to stamp out these releases. But I think it's pretty interesting maybe to talk a little bit about what we're looking forward to in the upcoming releases. Luke, what do you see happening for our roadmap? What do we expect to evolve, both in the component model and for WASI?
Yeah, well, I think now that we've got this release train flowing, that there's going to be a bunch of additions to WASI in this kind of 0-2 time frame that are, that already are in progress, already have been discussed for a while. Things like key value store and configuration and blob store and additions to HTTP. Like there's going to be a bunch more coming that can just, as soon as, there's enough, portable implementations and enough policy or portability that we can have a vote and then include it, and it'll roll out with the next release. So there's going to be a bunch of incremental improvements there, and also some incremental improvements in WITs around being able to express dependencies on other components. Right now, we have a lot of machinery for when I want to depend on an abstract interface that's like provided by a host. What if I want to depend on just some other component, and the interface is just implicitly whatever it's exporting? I just would like to import it. I would like to import SQLite. That right now requires a little bit of shenanigans, and we want to have first-class support for that leverages all this great OCI registry tooling that's been built out. And that was another thing that's been concurrent with all this work to date, is how do we publish our WIT as packages to a registry instead of just, I don't know, people copy files around and everyone tries to get it right, which is really annoying. And that was the mode we were in, and it's so nice that we're finally moving out of that world. So we've got all this great registry machinery. We're using distributed interfaces, which is like kind of a funny baby starting case, but like now let's do the big thing, which is like, yeah, let's have components importing other components, and have like a cross language package registry, that sort of thing. So first class support for that WIT I think will be also coming throughout the next year. And then after that, the big thing is this preview 3, and the big thing there is first class async and composable concurrency. And if you want to see an example of what this concretely allows, go to the WASI HP proposal and look at the 03 draft folder, which shows like the WIT says they can look once you have the stuff. And it's just so much cleaner, more understandable. And you can see like, oh, the imports are the same as exports. I can just, click them together. And then now I can chain HP proxies, like very powerful stuff. So that's the big thing, and a lot of ongoing work on that in the Composable repo. We're putting the proposal for how async concretely works in the Composable in parts. There's already one big chunk that's landed or merged into the Composable proposal, and I'm working on the streams part now actively. It's an add stream branch.
So looking forward to native async. Okay, well, that sounds like a lot of work in a lot of different areas. Lots of different projects come into play here. The implementations largely are inside the Bytecode Alliance organization, which is a nonprofit for building secure foundations for WebAssembly. Luke and Yash both are major contributors there. And so I'd really like to encourage everybody that is interested in this side of the world to contribute. Even if you're just a normal wasmCloud user, the cases that Luke just walked through, the OCI work, we integrate in the crates from Bytecode Alliance into Wash to make that really easy and feel like a native experience. The runtime that we build in is Wasm time. That's hosted inside the Bytecode Alliance. There are so many other also core WASM specification proposals that we didn't even get into. We stayed in the WASI component model space that also could really use some contributors hopping on. Yash, is there anything that you would like to give a shout out for implementations that would be a great place for new people to onboard and get involved inside the Bytecode Alliance or WASI?
Yeah, definitely. So we have like a number, like if you're interested in specifications, like I encourage you to like go read the WIT spec. I think is particularly accessible. It's very self-contained. But in terms of like Bytecode Alliance projects, a lot of energy is currently going into the WASM package tools project. Like a lot of improvements are happening there. I'm sure if you're like, hey, I'd like to learn more or figure stuff out, that's a pretty good starting point. Caro component definitely could use some love. There are reviewers for the code, definitely. But if you look through it, you'll probably be like, oh, I can see some minor improvements I can make. And that could be a great starting point if you know Rust. If you don't know Rust, that's a bit trickier. If you know C, by the way, WASI libc, you want to work on libc? We've got libc. But yeah, a lot of the projects are Rust. So even if you're like a beginner, I'm sure, it's not a bad place to start. But yeah,
Actually,
ahead.
I'd love to jump in and add that there's a ton of work happening in the Go space. We actually gave a few demos of that earlier today, where we built a component SDK to make it really easy to build Go-style WebAssembly components. But the idea there is to start taking parts of that and upstreaming that into the Bytecode Alliance componentized SDK. So most of these languages, actually, all the guest language producers, that's from Python to Go to JavaScript, all of that is also hosted under the Bytecode Alliance. So yes, the core internals, you're totally right, Yash. It's pretty rusty. But and I have a fan of Rustaceans loving WebAssembly here behind me, but I do want to emphasize that we've designed this whole thing to be language interoperable, and the guest producer tool change is a big area. Okay, sorry to jump in there. I thought that was important to add.
That's super helpful.
Yeah. So what can you make one major call to action for the folks today, and then I think we'll transition to some of our customer use cases.
One major call to action. Like, give it a shot. Like, try building something. We support a number of languages. I believe .NET is coming along nicely with the betas. We have Python, componentized Py. We have the Jaco project for JavaScript. Like, give it a try. Like, write something small, see how that works, see what works, what doesn't work. File issues if you'd like. We're here to help. We're very keen on people trying things out. So, if you're new to WebAssembly, just giving it a try, like that would be awesome. Yeah.
Yeah, specifically go to componentmodel.bytecodealliance.org and make a hello world in one of the languages, and then build a component and then run it in a browser with Jaco transpile, import it with just a normal import statement, and now you're doing cross-language development right there in the browser.
Brooks just dropped in a link that what Luke is referring to there is our component model book. Also, if you run into issues with the component model book and you want more documentation there, contributions super welcome in that case. Well, thank you both. I had a great time. I would love to keep chatting with you. If you would like, please join us on the wasmCloud Gather, where we're going to be hanging out later today. I imagine that other folks would like to quiz you, kind of like I just got the opportunity to. So thank you. Really appreciate it. I hope you have a good day.
Thanks.
Doug, I'd like to bring you on stage now. Hey, Doug, how are you doing? This is Doug.
Hey,
He's an engineer at Akamai, and I believe you're going to walk through a pretty incredible presentation. Hopefully, you've got share and everything enabled, and you can take it away.
Thank you. Let me get that started. Just a second, please. Sharing looks good.
Looks good.
Thank you. So let me get started. So hello, everyone. My name is Douglas Rodriguez, and it's a pleasure to be talking to you today. I'd like to present an overview of where we at Akamai see the world of edge computing evolving to, and discuss some of the new possibilities enabled by this evolution. But before I get started, I'd like to quickly introduce myself. I'm currently an architect in our cloud technology group. And one of my responsibilities is to help identify opportunities for our customers to take their distributed applications to the next level. And that can mean many different things, just as improvements in performance, reliability, usability, developer friendliness, security, or cost savings. And I also have worked as a developer in the past for quite some time, actually, and I have worked with many tools and programming languages, often building and operating highly distributed enterprise solutions. And from this background comes my passion for creating new and cool solutions. My favorite part about my job at Akamai is those moments when we overcome a technical limitation and enable developers to create new things. And today I would like to talk about how I see some of these limitations being lifted with the evolution of edge computing. But before I dive into that topic, let me talk a little bit about Akamai for those of you who may not be familiar with what we do. So over 25 years ago, Akamai created the concept of a CDN, a content delivery network, which allows companies to run their web applications at a global scale in a fast and reliable way. After that, we expanded into the security business with our web application and network layer security solutions. And more recently, we started to offer general compute capabilities in our core sites expanding our distributed edge to bring compute as close to end users as possible. But none of these solutions will be as powerful as they are today without the support of our massively distributed platform. Over those years, Akamai built a global network that is closely connected to pretty much any online audiences you may want to serve. In this presentation, my goal is to show you how this platform, combined with a new application development paradigm supported by WebAssembly and wasmCloud, has a huge potential to enable the creation of new, innovative solutions that were too challenging to implement in the past. Let me get into more details and explain what I mean by walking you through a reference architecture and presenting a couple of use cases. So I'd like to start talking about a new application development model where different components run in different layers of the edge. So we can bring some specific features to run closer to the end user, resulting in an optimal experience. In this model, a global router sends requests to the closest edge location available. At the routing layer, it's possible to perform some initial processing of the request, where we can implement authentication and authorization, perform checks on the request to identify malicious activity, or enrich the request data with information to be consumed by downstream components. Next, at the edge layer, we implement services that benefit from running as closely to the end user as possible. These typically include latency-sensitive scenarios that can be addressed without the need of integrating with multiple dependencies. One example, we're extracting a particular service into a component to execute at this distributed edge would result into noticeable improvements in the space of real-time APIs. Imagine an online collaboration tool, for instance, where user-generated events are broadcast to a group of users. These events can be processed at the edge, resulting into the lowest possible observed latency for users, while the other use cases that don't impact the user experience directly could happen at a core location. There are many other typical scenarios that can benefit from this type of architecture. One great example is gaming, where most online multiplayer games is critical to respond to player events quickly to offer an enjoyable experience. In that scenario, the separation would involve hosting the game server on the edge, closer to the players, focusing only on game state coordination. Once the game session ends, then centralized data processing, such as game progression, score tracking, that can happen at the core layer in this reference architecture. Another great fit is the field of generative AI, and I believe this topic was already covered today. But the interesting thing here is that there's a clear distinction between training and inference workloads. For these applications, training happens in a centralized location, as training has a heavy dependence on data and specialized compute capacity, typically GPUs in that scenario. On the other hand, inferencing, which is essentially the process of querying the trained model for answers, not only does not have the same data and hardware dependencies, but it is a latency-sensitive scenario. This clear separation between training and inference lets developers approach each problem separately, leveraging compute infrastructure that is optimized for each stage of the process. I hope I was able to demonstrate that there are many cases where we can optimize experiences by running specific parts of a bigger application in the edge layer that makes the most sense. Because one important decision to be made when implementing this type of architecture is to choose where a component fits best. As when running on the distributed edge, there are different capabilities available depending on which layer or layers the code will run on. As an example of what that continuum of services from edge to core would look like, this diagram shows the vision of the Akamai Connected Cloud, where at the edge layer we build on top of our extensive global presence to place compute resources as close as possible to end users, while at the same time supporting this hyper-distributed model with core locations in traditional data center deployments, providing a great variety of features and virtually no limits to compute capacity. Naturally, as the Akamai Connected Cloud evolves, we certainly expect to support most features on all layers, with the goal of the whole platform being as homogeneous as possible. And in order to harness all the power that this distributed model offers, application developers need to be able to reason about all these layers and the various capabilities using a consistent and uniform abstraction. I really believe that WebAssembly and wasmCloud are very compelling technologies to effectively leverage distributed platforms. And these are some of the main reasons why I think WebAssembly is so powerful. I know there's not much new here for some of our audience, but let me highlight why I think these aspects are so important in the context of an edge native application. So Wasm code is portable. It can run on the server, on the browser, and lends itself well to a model where we can run on the distributed edge, core data centers, or a combination of both. It's also polyglot, resulting in the freedom for developers to implement their solutions using the best tool for the job at hand. It's lightweight, small binaries, no dependency on SDKs, and efficient dependency management via Wasm's component model. And for efficiency, there are two aspects I would like to highlight. First, efficient resource utilization, allowing many workloads to share the same compute capacity. And second, but certainly not least importantly, cost efficiency, minimizing the need for idle and over-provisioned resources. This technology is a great enabler, for mobile and IoT solutions, as the portability of Wasm is a great fit for execution in resource-constrained devices. And finally, but certainly not less important, security. Sandbox model lends itself well to multi-tenancy and presents a very interesting paradigm to implement applications that are secure by default. So as you can see, I'm not short of reasons to feel excited about the possibilities in this new model. And if you like the concepts that I presented here, I would like to invite you to try it out on our platform. So on this slide, you'll find a couple of links. The first one, you can get started on our compute platform with $5,000 in credit for business accounts, or if you create a personal account, you still can get $100 of credit to use. And on the second link, we have instructions to set up wasmCloud on LKE. LKE is our managed Kubernetes service. It's a pretty straightforward setup, and with the credits and the setup instructions, it should be up and running in no time. So that's it. Thanks for the opportunity to share a perspective on the evolution of edge computing. I'll be happy to answer any questions we have now.
Yeah, Doug, thank you so much for the presentation. It's really inspiring seeing such a distributed network and then, combining that with wasmCloud.
Thank you.
Yeah, I had a kind of a broad question, so I hope this speaks well to the presentation and to other people who have watched. When looking at this like far distributed edge and wasmCloud and what Akamai is doing, how do you go about like architecting applications in this way? It seems like it's a totally different paradigm than the public cloud or just containers.
It is, yeah. It's a great question. Let me try to highlight some things that I think are not too different and things that make this a really kind of unique paradigm. So I will start with the shared infrastructure. So if you think about the basic development of a web application where you have client and server, and unless you are fortunate enough to be able to leverage the same programming language, let's say you're running a Node.js application, unless you're in a model like this, you typically have to deal with more than one programming language. Or in more modern deployments, not only you have a web client, but you have devices. You have to write your iOS or Android client, for instance. So that typically requires you to use more than one programming language. So in that model, you would have to deal with a number of different dependencies coming from different worlds. Leveraging Wasm, this type of solution, should let you reuse some of this logic implemented on top of WebAssembly, which you can invoke and consume from different outer programming languages. So that would be one difference. Another aspect is the separation of core layers, right? I think that is the most important thing that I wanted to highlight in this presentation. So you shift from a traditional deployment model where you have one data center or a few data centers and most of your compute capacity there, and you route all your clients regardless of whether they're running on the browser or on the device or anything else. all of these are are processed in this handful of centralized locations. What we're trying to do here is not be bound by this handful of locations, but be talking about hundreds or thousands of locations and abstract this type of deployment away. So from a developer perspective, I don't have to choose, I want to deploy in this data center or that data center. I take the code, load it into my distributed platform, and let the platform and the routing rules that I have in place figure out where is the best place for it to run. So this would be another aspect. And another thing I would like to highlight is this really neat concept of being able to kind of cherry pick, identify isolated use cases that do benefit from running closer to the user. Typically, we're talking about latency sensitive applications. One one space where this problem shows up recurrently is in the optimization of web applications. For a lot of businesses, if you can make your web page load a fraction of a second faster, that tends to reflect into better conversion, improved revenue for you. So a lot of businesses are really looking for more tools to be able to make their web applications even faster. So in that case, if you can factor out one specific feature, let's say a customer personalization page or a set of recommendations, and make that run at this edge closer to the user, leveraging this low latency efficient location, running compute as close to your end user as possible, you should have a very powerful tool available to you to implement this kind of solution.
Now,
I
Doug,
hope that answered the question. Yeah.
Doug, this is Liam Randall. I would like to maybe point out to folks that, well, we just hosted you on Cloud Native Live a few weeks ago with Adobe, where you highlighted an early vision for some code development that's happening there. And you have an upcoming speaking role in the next few months, don't you, where you're going to be sharing more details about some of that exciting work. Is that right?
That's correct. Yeah, we spoke at CNCF Live. That's recorded for those who hadn't had the chance to watch it. I talk about these ideas in a context very similar to what was presented today. And we do have a presentation scheduled for wasmConf. It should be happening early November. In partnership with Colin from Adobe. You're going to be seeing his presentation later today. And yes, the overall idea is to present an evolution of this. As you can tell, there is quite a bit that's in the works, but we are very confident that we have a very interesting technology that we're able to evolve and do more and validate and have reference implementations, have use case references for these scenarios that I described, running these applications in a very distributed fashion and leveraging this distribution to make sure that we can present optimized experiences to our users.
That's incredible. And, Adobe was one of the first early pioneers to embrace WebAssembly in the browser. There's an incredible Google blog post from the Chrome team about the work they did to enable Photoshop there. So it's maybe not too surprising to see Adobe continue to be such an aggressive technical pioneer on the server side and even on emerging edges. And maybe I'd do a call out to anybody watching at home live now or later that if you're interested in exploring code development of what a distributed WebAssembly application would look like with wasmCloud, feel free to reach out to us on Slack. We're working presently with Doug and his team over at Akamai to help customers pioneer the space. So feel free to reach on out. Brooks, I'll turn it back over to you.
Yeah. I was kind of keeping an eye on things, Doug. I didn't see any other Q&A come in on the Zoom, so I think that's it for now. But thank you so much for coming on and sharing from the Akamai perspective. Why wasmCloud is so cool, how we're pretty aligned on the full distributed edge and the promise of that.
Pleasure was mine. Thank you. I'll be sharing the slides and the links afterwards. My LinkedIn page is there. If anyone has any questions, I'll be happy to continue the discussion there. Thank you.
Awesome. Thank you so much, Doug. Yeah, anybody who has further questions, of course, please reach out to him on LinkedIn as well. But he is in our wasmCloud Slack, so more and more there too. Well, I have the distinct pleasure of welcoming Jochen and Tyler from Machine Metrics Platforming Engineering team. We've done a couple of collaborations with you guys over the past couple of months, and I don't want to spoil anything, so I'll just hand it off to you all. Take it away.
Yeah, thank you. My name is Jochen Rau. I work for an IIoT company called Machine Metrics. I'm with my colleague Tyler. He will also do some of the presentation. So we are we're a company that connects to thousands of factory floor machines that produce parts, so this discrete manufacturing. And we have hundreds of companies that use our SaaS platform to look at the data, look at how their machines perform, and optimize their machining processes. And so what we talk about today is a little bit how we use Wasm and wasmCloud on our edge devices and in our cloud. And I let Tyler take it away from here.
Yeah, for sure. So we're going to talk really quickly kind of about what led us into this technology space, and then go through a little bit of a good use case that we built out a proof of concept using some of this tooling to support. Talk about some of the architecture that this enables and where we're looking to continue to build using some of these great tools. And we're really excited to have the opportunity to be here today to show a little bit of what we've learned and just some of our passion for this community and the great tools that they're providing. So what you can see here, that little picture of the little box is an edge device. That's what what Johan has in his hand there. That's what we use at the factory floor to connect our machines to. So that's kind of our edge compute layer that currently ingests all our data, manages some other services for running on the factory floor. But there's a lot of restrictions there, namely just some of the security stuff, just around like our customers. We have mom and pop shops with no security, really not a lot of good posture there, all the way up to companies who are doing manufacturing based on government contracts. So we kind of have to live with an expectation that there's not a lot of security, which is where WebAssembly in the component model comes in handy, providing a really great sandbox environment that allows us to provide some great guarantees just right out of the box. Deny by default is awesome. Just add in what we need. Works really well for us. And then in terms of resource allocation, these devices are not very powerful. So we're talking low memory, low CPU. We can run into bandwidth issues in certain shops where they're running like a really slow 3G network to make this connection happen. So things move slow. And again, that's where WebAssembly and the efficiency that we can find there really starts to come in handy. And then where wasmCloud really steps in is that one, we're using NATS already, so we have a good understanding of how that platform works, and we can quickly just build on top of it. And then also we can't do Kubernetes at the edge right now, just since we're running a system there that requires everything to run in Docker. So then you run into this weird inception of Docker running Kubernetes, running Docker, or just container platform within there. And then if we wanted to be able to just run Kubernetes bare metal, we would have to reflash a lot of our devices. It's a long process that would require a lot of time with our customers to make it happen. So it's not really feasible, making something like wasmCloud really one of our only options in this space. So now we'll go into a little bit of our example here. We're going to talk through. So what you can see here is a machine lathe going through and cleaning off this part that's being made. And so these tools can be very expensive. And so, a value proposition that we can add as a company is to monitor the tool and based on the telemetry data coming in, be able to tell you when your tool is going to break so you can stop it at the right kind of middle ground between, not breaking your part, which you can eventually see here in the GIF, which could be very expensive because you can scrap that part, and that part could have been on the machine for hours, wasting a lot of time, and then not to mention the material of the part. But on the contrary, the tools are expensive. You want to try to get the most out of their life before you then replace them. So yeah, you can see eventually it'll smash. But this process, we've started to work out a feature around tool monitoring, but requires us to process high frequency data, specifically at the edge, so that we can know when the tool is going to break, try to save that part, and stop the machine. So that's where low resources and some of the problems that we kind of have in our current space really start to rear their ugly head and become a bottleneck and prevent a great feature such as this. So that's we went into looking at downsampling within this space just as like a proof of concept for a lot of the tooling. So like I mentioned, resource constraints. We want to be able to use high frequency data to provide this value proposition. And that's challenging for compute at the edge. Also other implications around, we're going to actuate on the machine. We need to make sure, again, that our security model is very, very rigid so that we don't have any malicious actors coming in here and taking action on a customer's machine. And then as well as like high frequency data, the kilohertz level can be difficult to visualize in a lot of common tooling. We can show in another example, in one of our examples, just like using Grafana, it will just lead to running out of memory. You freeze up in the browser and everything crashes. So downsampling is a really great way to go about this. So we use the largest triangle 3 buckets algorithm modified for a stream so that we can capture this data and still represent the same curve and capture those highs and low points, and as things change quickly, so that we can not only just visualize the data, but use it for something like tool monitoring. So we wrote out this proof of concept using Rust, compile it down to a WebAssembly component, and then we deploy it on wasmCloud using WADM. And here you can see here in this little GIF, just kind of like an example of what the downsampling looks like through this algorithm. So from 5,000 all the way down to really just like a few dozen data points, it represents the same curve with about the same fidelity. You start to lose a little bit, but the same like highs and lows are there. So to the eye, it can resemble a lot of the same thing. And then in such an algorithm such as tool monitoring, you can still get the important points out of it that you need.
Yeah, so, and I'm going to talk a little bit about the architecture of how we set up the proof of concept, which gives an idea also how we can use wasmCloud in an edge and cloud environment, in a mixed environment. A little bit more into the details here. So like we said, we have Nats already running. So it's running on the edge device as a leaf node. If you know Nats, you know that a leaf node is basically what you would use to connect then to a cluster that runs in the cloud. So we have a Nats cluster running in Kubernetes here on AWS. And we have a Nats cluster running, or a Nats leaf node running on bare metal, basically on the edge device. We have different streams in Nats SCADA. When you see the word SCADA here, that's our machine data. That's basically loads, or whether a door is open or closed, what the tool load is, and so on. This is SCADA. wasmCloud provides us with the other topics, and we have also configuration, a stream that contains, or key value store that contains configuration, and a key value store that contains a cache. It's all in Nats. That's distributed. So what we did was we coded a data sample in Rust, which is a WebAssembly component that runs on a wasmCloud host. It's managed by WADM that you might have heard earlier today, which is the manifest basically that we describe how our application should run. And we use two of the providers that runs on the host that connects us, or lets us connect to messages from Nats, and the key value store on Nats. And this provider is basically out of the box. You can use out of the box providers, and we could just conform or use the API that comes with those providers. So what you can see here on the left side, where it says high frequency HF data. So we read that high frequency data into the data sampler. we sample the data. We have to use in that algorithm a cache, and therefore we buffer some of the data from the data sampler in the cache on Nats. That's where we use the Nats key value provider. That's a store in a distributed way the values that we already saw. And then we read it back, sample the data, put the sampled data back on our machine data and SCADA data, and then make that available in our application. And there's a little bit more to it with the configurations on that we can skip for now. But on the other end, then on the cloud side, we have the Grafana instance running in Kubernetes that can read the sample data. And we can also have our dashboard that runs on a laptop. You see that in the center, right, with a little laptop here. Directly read the sample data from our SCADA topic into our dashboard. Everything is managed by WASM, and so we can centrally manage the whole application and distribute it. Now, demo time, and I hand it over. You can share your screen, Tyler.
Yes.
Go out of it and stop sharing. Let me stop sharing here.
Perfect. Yeah, so I'll move through this pretty quick.
Okay.
But just to make sure, we went on Cloud Native Live with Taylor and shared this in a little bit of a longer format, as well as KubeCon in Paris. And so those are both recorded. So if there is more detail that's desired, then it's definitely available. And outside of that, we're happy to answer any questions offline. But so right now we have some high frequency data that's coming through over NATS. So you can see all this stuff is flying through. And then I can use.
Gotta share your screen.
Oh, it is sharing. Is it not?
Oh, okay. Fair enough. Yeah, okay.
Okay, perfect. So then I have a little script here that will start up the sampler. All this is doing is just starting up wasmCloud, WASM, and then deploying our manifest using wash. So that will use the manifest that we have here. This is still using a little bit of an older version, so it would look slightly different on the 1.1 world, but really kind of like the same idea, just defining the pieces that we need here that Johan just showed. So what that will do, we can take a look. Wash app list. See, hopefully we'll get this to come up soon, but we would be able to subscribe on sampled, and we can see now that the downsampler component that we have running within wasmCloud is sampling that data. So we're getting that at a much lower frequency, but still representing the curve like we talked about. And we can show that a little bit in a UI that we created. Oh no. I have a video somewhere. Interesting. Okay. All right. Well, so what this would show would be the two curves. We can represent that really pretty similarly if I was to split the pane to the right, and we did a NATS sub on sampled, and then also NATS sub on raw. So you can, what I was going to show via the UI is just the curves being plotted out. So you can visually confirm that it's showing the same two curves, but this is a pretty good example of the two data points coming in. And then what Yo had mentioned too around some of the configuration, right? So it's great that we're able to use the NATS key value provider from wasmCloud so that we can have distributed configuration. So from that same browser window, you can tune what your max lag would look like. And if we take a look in our key value here, we have, just like what Yo had mentioned, we have some caches for the last event in the buffer, but also the max lag. So if we do NATS key value get on the max lag, we can see what that's tuned down for in milliseconds there. And this is super powerful because you can have this configuration completely distributed. So you, as someone who's looking at this in the browser or from anywhere, can tune your configuration that's running somewhere totally else. You have no idea where it is. And, in this case, right, like running at an edge. So a lot of that's abstracted away from you. It's just kind of dealing with the key value provider, but super powerful abstraction and distribution. So now I can kick it back over to Johan. He can talk a little bit about some of the architecture direction where we're headed.
Okay, can you see my screen again?
Yep.
Okay, so what that proof of concept showed us clearly, and that's basically what sold it in the company, is that it is possible. It gives us the tools to distribute computing where we need it, right? So we're not bound to a cloud environment. We can distribute it to the edge or the cloud. So it doesn't really matter where we run our compute, other than being bound by the resource constraints, right? So the data is completely distributed. So we have access to our machine data wherever we need it, and we have the compute wherever we need it. Maybe we need less latency, so we can deploy it to the edge device. So since we were able to show clearly with that proof of concept in our company that this is possible, it became really attractive for us to move to the next step. And I want to show you a little bit what that entails here. So here you see the same picture as before, right, with our edge environment and our cloud provider. And now we have a new project which monitors tool monitor events. Like once we realize, okay, there is a tool wearing out, we want to be notified, we want to take action, we want to send an email to the operator, we want to send an alarm to our dashboards and so on. So it's a very kind of distributed way. We produce a tool monitoring alarm at the machine level, and then we send it out. So right now, how that works is like it's shown on the screen here. So on the left side, you see the machine with an adapter, and the TM stands for tool monitoring, putting tool monitoring anomaly events on our machine, on our SCADA stream, and pushes also machine data, regular machine data, continuously into the SCADA. And on the cloud side, we use Kubernetes all through. We have our database running on Kubernetes, so we're using that infrastructure quite extensively. So we're Kubernetes shop, and there's a pod that syncs it into Postgres and makes those anomaly events available via Hasura, which is a GraphQL implementation. So it's a GraphQL API, but also directly to our dashboard, running on an ECS instance still. And that reads it from Postgres. And then it gives it to a notifier agent, which is an AWS Lambda. And that's our current architecture, how that works, right? And our next step is now to re-implement that and extend it using wasmCloud and WebAssembly components. So here's how the first step looks like. And there's a monitor and notifier that uses the NATS provider or the messaging provider to monitor for those events, and will then call HTTP or can get machine data from Hasura and also call out to the notifier agent. So we're not replacing in this first phase our existing Lambda, which has a lot of built-in capabilities, and so we're just basically placing the first little step into our environment. And here you see the wasmCloud host, in contrast to what you saw before, runs actually in Kubernetes. It uses the wasmCloud operator, right? And we are reusing all our existing kind of infrastructures, and we are not changing fundamentally the way we operate those things on Kubernetes, which is a very good point of selling it within a company that already uses Kubernetes. You can say, well, we're just running a wasmCloud host and doing basically running components on it, but nothing around it changes much, right? And the next step that we're going to do is then kind of re-implementing the notification part of it. We can have email and Twilio notifications. We can also provide that with as just another message where it picks up in a very different place, those notifications. So that's the next step, getting rid of it, right? And then the final step, and I kind of flip back and forth a little bit here, would be to, or not final step, but we want to enable our developers to use GraphQL in a very comfortable way, in a standardized way, without knowing anything about the whether you send a HTTP request or whatever. And so here you can see we're working currently on that, adding a GraphQL component that lets you just call out to this specific component. So you glue those things together, and you can compile it in one single component later on. So in a more library style, and that's very helpful for our developers that should be abstracted away from all the underlying infrastructure like NATs and so on. So now I've talked a little bit about the way we want to decide later on where we want to place those compute, so runtime, monitor, and notifier. And we want to actually place that, and I'm going to flip back and forth a little bit here to see, so you see the difference here, right? So if I flip back and forth a few times, you see that we're moving the monitor and notifier to the edge device, to our edge locations, and still wasmCloud host, right? But this time running bare metal on a custom supervisor that we wrote, right? So we're taking it, we're not compiling the GraphQL component into the whole application, but we are running the GraphQL component still in the cloud here, because we are not running a database on the edge devices. So we still have that capability, but this time we're calling it through wRPC. Right? For the developer, nothing will change here. Right? Still calling the same API functions, still sending a GraphQL query, getting back a result, and it's in a completely distributed way. So we can basically have the freedom to decide whether you need low lag kind of responses, and where do you need a kind of resource intensive applications like Postgres. So we can move things more freely, and that's a real benefit of wasmCloud and WebAssembly, that you can basically make architectural decisions that have more freedom, right? And they're not bound only by language barriers, for example, by team barriers so much, right? They're mostly around languages. Our edge team uses C++ mostly, right? And Python to some extent. And in the cloud, we use TypeScript and JavaScript, but that doesn't really matter anymore because everything will compile down to a component. And that's a real beautiful aspect of it, right? It's very powerful and also a very good selling point for us. Finally, what we're doing right now, we're developing all those base components and base libraries for our developers at the moment, and also in parallel the monitor notifier part of it. But mainly, we're laying the groundwork for an absolute accelerated development experience for our teams here. Right? Any questions? I think we went really fast on that. Let's see. That's the last slide. Any questions so far?
Hey, you kind of ran it perfect. This is really so impressive to see like wasmCloud employed at like such a specific use case. It always gets me excited. I have kind of a stepping back question a little bit, because what really captured me at the beginning of this is you have a requirement that you cannot run Kubernetes in your edge location. And so like my big question, I feel like a lot of people at different companies or maybe their own, home lab or whatever, just run into this where they can't run Kubernetes or they don't want to. How did you find wasmCloud and then get started with this as your to do this downsampling example or this dig application?
Well, it originated in the Wasm Day at KubeCon in Amsterdam. I think 2 years ago, or 1.5 years ago now. So where I've just happened to hear a lot about Wasm, WebAssembly, and wasmCloud. And it made totally sense from there on, made totally sense for me we looked at different technologies, of course. Not naming names here, but wasmCloud was very attractive to us because it had the right step into a new paradigm. Right? So it enabled us to basically abstract away the thing edge versus cloud thinking, in that it uses NATs underneath, which we already use, right? And it has the right paradigm of doing away with that. It's just you're thinking in an application, you're thinking in interfaces, right? And you implement against interfaces, and not so much like, oh, you're supposed to run it on Kubernetes or the wasmCloud host, right? Or you're supposed to run it bare metal. So it gave us the freedom to do that. And at the time in Amsterdam, it was the pre 1.0 stage, so it's fast moving, and it's still fast moving, which is good in some sense. And I thought it's really going in the right direction for this specifically IoT environments where you traditionally come from this edge cloud paradigm, and we wanted to do away with that, right? We wanted to focus more on apps again instead of the deployment environment. So that's what's the main motivator.
Yeah, and this is maybe a little bit of like having drank too much of the Kool-Aid, but it's something we're super excited about. And we just come back to it time and time again. I mean, just in an offhand conversation this morning, Johan and I were like, there's just so many value props that you get out of the box with wasmCloud. Like, right, as a platform team, we can provide our developers with a lot of the tooling that they need to really only focus on writing features, handling business logic in small modules that we can reuse. And that's super, super powerful, especially in an organization like ours, like Johan mentioned, where we have teams that they do certain things in certain places and they have to think about where things are going next. And we can really start to just forget that. And wasmCloud opens the door, unlike really any other technology.
Yeah. And one other thing that I want to mention is that at the time in Amsterdam, there were things that we would consider we couldn't use it in production, right? But there was secrets management and things like that. And you opened with that today, and I think that's a absolutely powerful tool that not just enables us to use in production, but makes our architecture much better than in the way we can handle secrets and credentials and so on. So it's kind of going. The community turned out to be, and I talked to you folks quite a bit in the very beginning, and it also is about the people, right? It's not just the bare technology and tools, which goes in the right direction, but also a bunch of smart people behind it, and that's also a good feeling, a good selling point in the company, that this is backed by a good community, right?
Look, you guys are awesome. Thank you so much for the kind words. I mean, you've helped us just as much as hopefully we've been able to help you with, some of the new features and just listening. I don't know. Kool-Aid sounding kind of good. No, all right. Jochen, Tyler, I would love to continue asking you questions and just talk all day. I think we are going to have to move on to the next speaker, though. So thank you again so much for taking time out of your day to come do the session.
Yeah, we'll be in the Hangout later.
Awesome.
At least okay, but
sounds great. Well, you heard it here first. Make sure to come to the Gather Hangout. You can come ask these guys all the fun questions you have about running wasmCloud on the factory floor. And with that, I think we can move on to our last but not least customer user demo for today. It's my continued pleasure across this entire day to introduce Colin Murphy from Adobe, who's been bringing wasmCloud to Adobe's Kubernetes infrastructure. I, again, don't want to do too much spoiling. So, Colin, I'll just go ahead and give it to you. You should be able to share screen and all that stuff.
All right. Thanks, Brooks. Yeah, everybody can see it. I stupidly updated my my operating system right before this. Okay, so everyone can see this is Adobe Express, which you can do presentations from. Just throwing out that out there, working on this. Okay, so my name's Colin Murphy. I work at Adobe. I think most of you know that by now. yeah, so I'm going to talk about C plus wasmCloud. And hopefully we can slide. Okay. So we don't have a lot of examples in the wasmCloud examples of C, or we have no examples in wasmCloud examples of C. We have no examples really anywhere for C, a C WASI service. I did, in the course of this, did find one example in a gist, but other than that, there really is not a lot. But we should, we should have C and C++ examples. We should, because first off, in the embedded space, in the applications, desktop application space, in the gaming space, C++ is still the king. All of the Adobe desktop software, all of our WebAssembly is written in C++, with the small exception of the Content Authenticity Initiative, which is written in Rust. And we have a lot of WebAssembly users out there for Inscription, and we want them to write WASI applications as well. And then another reason why C and C++ is a good thing to support in wasmCloud is because it's supported in WASI. Although not many examples, but there's the WASI SDK, and it's been built into the Clang compiler, so it's there. So we just have to kind of expose it and give good examples for people. The use case that I made for this example was PDF. So I wanted something that was technically challenging, a little more than just hello world. And PDF is, because it's really taking something you'd send to a printer and putting it into something that can be rendered on a monitor. So back from the 90s. I've actually got behind me over here is the guy who came up with it. So it's technically challenging. There are lots and lots of implementations. They're all written in C or C++, and they're of varying quality. And third, this is something that we probably want at Adobe, but there's a lot of PDFs in open source format. There's a lot of use cases for running PDF functionality. We call them verbs on the edge and in various places. So that was why I thought PDF was a good example. I'm just going to go through it. Just going through how I did it. I defined a PDF library. I wanted it to be open source so I could put it out there on the web. I wanted it to be somewhat functional so that I wouldn't get in trouble, and by changing it too much. And it had to be written only in C just to make it easier for Clang and WASI. C++ with a lack of exception handling and various things in WASI. It's just easier to just go straight C. Although not impossible to do C++, but I only had a few days to do this. And it had to be able to open PDF files, which is actually something that not a lot of libraries out there do. A lot of creation libraries, but not a lot of just opening an existing file. And I wanted to be able to give it a PDF and have it spit out the text of the PDF. To generate the bindings, so I used with BindGen, just like it's built into Wash for the other languages, but not yet for C. So I just had to generate the bindings for C, and then the third part is get it working, which is always 99% of everything. There was that one gist I found for implementing HTTP incoming handler. That example that just actually did not work, but it was pretty trivial to get it working. The real challenge was modifying that PDF library. So all PDF libraries use file handles because it's been around for 40 years, and so there wasn't a lot of working memory when PDF libraries came out, and PDFs can be very large, and so they're used to working with PDFs on disk. That doesn't work for WASI. First off, it gets kind of complicated because we have OpenAT, right? We don't have the full suite of file opening and writing capabilities by design. So I had to use a memory buffer. So I'm gonna post the whole PDF, and then it exists in a memory buffer, and then I needed that PDF library to work on it in a memory buffer. And I lost my mouse. Yeah. Okay. So as I said, that was kind of the big challenge So just emulating what a file handle could do. So fseek, lseek, open, read. I didn't do writing, but kind of do that. The standard sort of things. Maybe we can build those into, build some kind of functionality into the WASI SDK or wasmCloud. The other kind of challenge was that when you generate the bindings, and maybe I'll show that if I have time, there are a lot of Rust concepts. Well, there's the main Rust concept of owning and borrowing, and those create duplicate functions. I don't know why fown got in there, sorry. It's just supposed to say own and borrow methods and types. And there's also lack of namespacing, right? So I can't, so the methods and types of the package get, well, I guess prepended is the, added to the beginning of the methods and types. And so it makes it so it's kind of harder to, it's harder to kind of make an example that everyone can use when the name of your package is on every single type and method. But I did, there's a PR I've added to the wasmCloud example, or I've opened to add a C example. So you can all see that. And then dependencies are always really hard in C and C++. Anyone who's done C and C++ knows that. Lots of times there'll be one build tool chain for one package and another for another, and it can be really, really terrible. So really what was nice with this library I chose, PDF.io, the only dependency was zlib, and you already know that works in WASI. So that was very fortunate. I do want to demo, and then if we have time, I'd like to go over some of the kind of in-depth, a little more of the challenges I faced. So everyone can see still. Somebody Slack me if you can't. So here, yeah. So we've got, I've got the PDF text. I made a WADAM file, and just really copied it from the Rust example, hello world. And I've just got a little component, and I've got the server, and I have a, I just have the basic PDF I'm going to give it, because it was actually a limitation in the library, not WASI, that this thing can't handle pictures or any sorts of bounds or anything like that without crashing. So this is a very minimal example, and then here we go. I'm just going to send that post, and yeah, and so I get out. This is, as you can see on the bottom, this is a test PDF. There's more in this example that I included. There's more in this little thing, and also I included in the example in the PR just to kind of work through the how what's in that request, what that request comes in as, because it's C. You're doing some. It's not nicely packaged for you, the headers and such. So here is the. I will. Okay, having a hard time. Sorry. Okay. I was sharing. I had a window because that's how I did the presentation. But whatever. Okay, so here it is. Anyone can go grab it. And you'll find that it's all in here. There were some changes to PDF.io, but you kind of see that this is a lot more. There's just a lot more stuff you have to deal with in C. A lot of like pointer casting, things like that to read headers. So it's not as easy to get started. And I lost my presentation. Okay, so I'll I don't know. Are there any? Maybe if there are any questions, I can talk about those now, or I'll try to get my presentation back. It was Chrome's fault, not Adobe Express's.
Good save there, Colin.
Yeah. Here it is.
Yeah. Okay. Go for it then. I'll hold my question.
All right. Thanks. Thanks, everybody. Right. So was actually me probably pressing Command W. Okay, so there were a few, and maybe this will spur some questions, but the challenge I really banged my head against was LLVM shadow stack memory. I kept rolling over the pointer on the stack because there was just so much the depth of function calls got to the point where for a 32-bit system with a 1 megabyte stack, it's pretty easy to roll over the stack pointer. So it's a little confusing because there's a stack pointer in LLVM and there's also a stack pointer in Clang, and you have to make sure you set the right stack size. So thanks to Pat Hickey on that one. The other thing Brooks helped me out with was the blocking read and write. That's in the Rust examples, but I forgot about that. You actually can only read up to, I think, 4 kilobytes at a time in the HTTP handler. So you have to keep looping, and then when you write, you have to keep looping through and writing out. Using Wasm times serve was really useful. I know we're getting there with wasmCloud host, but Wasm times serve was a little more verbose when things went bad. And then I work on this on my Linux machine and on a Mac, so that could be a challenge as well because Xcode and system libraries and stuff like that are in different places. But I made it so it's all in one. It's an all-in-one package. You don't have to. There are a few things you need, but there's just a make file, and it just builds everything. So it should be not intimidating if you want to test it out. And maybe somebody can get PDF.io to be able to actually take text from complex PDFs. All right, that's it.
Colin, this was super cool to see. I don't know, kind of just like the whole flow through like use case to finding PDF library to turning that into a component. I'll be the first to thank you for stubbing your toes so that we don't have to. I did want to ask, maybe let me know if you can share this. What's the plan for this component? Like now that you have this component that's written in C and processing PDFs and you can deploy it on wasmCloud, where are you going from here with this app?
Yeah, so what I'd like is to hopefully get I have some traction, but build some momentum within Adobe for our own proprietary PDF libraries to build this out into a component. I don't want to say too much more, but if you can filter out if you just are looking for PDF text for a given application, passing an entire PDF is expensive in network costs and user time. So if we can process that stuff out on the edge, especially for mobile or small devices, that can be really useful. We have, as I said before, we really think of PDFs in terms of different verbs and different actions with PDFs, and if we can compile each one of those actions into a different WASM component, it should give us more flexibility.
Yeah. Quick, maybe dumb question. How big did this component end up being?
Oh yeah, I didn't. Sorry, I had my day job got in the way. Too much Express. I got it to 947 kilobytes, but I did not compile it. I did not optimize compile it. So it's less than a megabyte without anything stripped out. So hopefully much smaller. Sorry, I didn't mean to do that.
That's super. I mean, that's great to hear. Like a Rust component, I think usually comes in at about like 2 megs, and then once you strip debug symbols, it comes in, anywhere from like 100 to 200 kilobytes. So I bet this one is probably pretty small once you do minus. That's pretty cool.
I'll see if I'll have it for come to the Hangout, and I will have stripped out everything and optimized build it.
Yeah, you gotta come to the Hangout to see the
Hangout
final component.
Yeah.
All right. Well, let's see. I didn't see any additional Q&A. But I think we can go ahead and wrap this up and start moving on to the Hangout. Thank you so much, Colin, for again taking time away from the day job and away from what you're doing to present here. It was really nice.
Yeah, thanks.
So, folks, as we kind of get to the end of the first part of wasmCloud Innovation Day, again, thank you so much for coming today and listening to what we've been working on over the past couple of years, over the past few months. Really, it seems like everything has skyrocketed in an innovative direction. We want to thank everyone for coming today by offering you some wasmCloud swag. So if you want a t-shirt that's super cool, like this one, wasmCloud on the front and on the back, you can sign up. There is like a form here at the end of this QR code. We also have this on a link. I think it's wasmcloud.com/swag. We want to, we offer this to our community members and sorry, I missed the slide for some reason. We offer this to our community maintainers, our community members, and we really want to extend this to you folks who have come and spent the day with us. I mean, there have been I think hundreds of people who have been watching on the webinar, on our different social channels, and that's hugely inspiring to me. So if you want some swag, you are welcome to it. But even if you don't want a t-shirt, please come join us on the wasmCloud Slack. This is where we are hanging out on the daily, talking about new innovation in the WebAssembly and the wasmCloud space. You'll get nice and handy reminders for wasmCloud Wednesday when it's time for you to join. And all of us, the people who have been building things with wasmCloud, the people who are maintaining the project, are hanging out there again on the daily. So please come join. Slack is accessible. There's a QR code here if you wanted to pull out your phone, but if you go to slack.wasmcloud.com, that should bring you right in. And if you lose that link or forget it, you can just go to wasmcloud.com and we have a link down at the bottom of the page. So thank you so much for coming to the first part of this presentation, full talking at you for a long time. We want to be able to turn this over to everybody who came and is a part of the community now. We are going to be hanging out in a collaborative gather.town space where we'll be doing co-working workshops. I am probably going to sequester myself off to a table at some point to work on a wasmCloud, a feature or two. There's going to be maintainers from the wasmCloud side, people from the Bytecode Alliance, the customers who presented their use cases today. So great time to come in, ask questions, and you're welcome to kind of come in and leave as you please. So just to give you an idea of what this looks like, as soon as you go to wasmcloud.com/gather, you'll get brought right into this redirect basically, and then pushed to gather. You can either join, this is kind of weird, I can see myself in both places. You can either join in the web browser or you can join with their native app. It doesn't really matter either way, but you can see I've got my little virtual avatar here with my wasmCloud t-shirt, of course. And really, I think that that's all that I had to share today. So I again just want to thank everyone for coming, attending, presenting today. We are going to take a quick lunch break for the next 20 minutes or so. I'll leave this up on screen so that folks can make sure to get to the right place, and then we'll see you in the gather space.
Hey, Brooks, maybe one little thing before we take off here. It would be amazing if we could give you a little round of applause for being our incredible MC today. You put in a ton of work, as well as all of our speakers today. I think what makes wasmCloud really special is the community. There's a lot of people that are out building WebAssembly, but I think this community really focuses on building better together. So thank you, Brooks. You're a wonderful leader and a great community steward, and an awesome MC today. Thanks. Celine, just to answer out loud, yes, today's session is already live at wasmcloud.com. I'm sorry, youtube.com/wasmcloud. And we'll be breaking up these sessions over the next few weeks and re-releasing them right on the Cloud Native Live feed as well. So the sessions will be out there. Look ahead to WasmCon in November, the first 2 days of the KubeCon week in Salt Lake City, if you aren't registered yet, where you can see a lot more great content, including talks from Akamai, Adobe, BMW, American Express, and more. Brooks, back to you.
Slide deck back to you. I'm gonna go eat a little bit of food, and then I will see you all in the gather space afterwards. So just a reminder, if you're watching live, we are going to end the webinar at the top of the hour, and we'll be continuing in the gather space where you can come, no pressure of a live stream or anything like that, and ask people questions, get to know the folks in the community and all that fun stuff. So I'm going to go off video, leave this up for until the top of the hour, and then I'll see you in the gather space. Thanks, everybody. Have a wasmCloud day.